Good morning, everyone, and welcome to the Royal Swedish Academy of Sciences. My name is Göran Östlin. I'm a member of the Academy. I'm also chairing its class for astronomy and space science, and I'm also a member of the Academy board, and I have been asked to give a little welcoming here today. So the Academy was founded in 1739 by people, among them Carl von Linné, and one of its earliest members was Per Wilhelm Wargentin, which you see there in the middle. The Academy has 400 Swedish members and 175 foreign members. What does the Academy then do? Well, one thing that the Academy does is to promote the role of science in society. But another important activity of the Royal Swedish Academy of Sciences is to award prizes and grants. And of these, the most well-known is certainly the Nobel Prize. The Nobel Prize in Physics and Chemistry is awarded by the Royal Swedish Academy of Sciences. And actually, the decision to whom to award the prizes are taken in this very room every fall. We have also the Crawford Prize, which every fourth year is going to astronomy, which you might be aware of. But the Academy also handles lots of smaller prizes and grants through its more than 100 different associated foundations. Another thing that the Academy does is to arrange for meetings about research policy, but also scientific symposia and meetings like the one we're having here today. Here are three former, now deceased members of the Academy, and I'd like to say a few words about them because what their scientific activity relates to the topic of this symposium. So the first one in the middle is Per Wargentin, and he was the secretary of the Academy from 1749 until he died, and he was its astronomer and can be regarded as a leading figure in Swedish astronomy at the time. He was son of a priest from northern Sweden and studied in Uppsala, earning a master's degree and becoming a docent there. It was during this period that he completed the work that brought him international fame, a dissertation called De Satellitibus Jovis by the 24-year-old Wargentin. In this, he investigated the orbit of Jupiter's Galilean moons with great precision. Another person, which is here pictured to the left, is Anders Johan Lexell. His work formed the basis for the discovery of chaos in the dynamics of comets. His name comes from the Lexe estate outside Gävle, although Lexell was born in Åbo, Turku, in Finland. He studied at the record pace in Åbo and Uppsala and became a member of Åbo Academy and was appointed docent in mathematics at the age of 22. He later moved to St. Petersburg with strong support from great mathematician Leonhard Euler, where he observed the transit of Venus in 1769 to determine the solar parallax, the measure of the distance to the sun. However, his reputation is primarily linked to a comet discovered by Charles Messier in 1770. Lexell discovered that this comet had been captured into its orbit by a close encounter with Jupiter 3 years earlier, something now well known but unexpected at that time. Since then, the comet has borne Lexell's name. As a result of this discovery, he was also elected a foreign member, number 84 of the KVA, the Royal Swedish Academy of Sciences. Finally, to the right, we have Hugo von Seipel, who lived from 1873 to 1959. He was born near Stockholm and became an astronomer at Uppsala Observatory, where he held a professorship in astronomy from 1920 to 38. And in 1915, he became a member of the Royal Academy. He was a theoretician active in astrophysics and celestial mechanics, And his work led 1909 to a publication whose results are still, and especially today, highly regarded in solar system research, and will surely be discussed at this meeting. It concerned the motion of periodic comets, for instance, Lexell's comet, and demonstrated the possibility of large-scale oscillations in cometary orbits. This could cause comets to plunge into the sun or cause small bodies to leave their safe haven in the Oort cloud and fall into the inner solar system, lighting up as beautiful comets. And astronomers have now for long referred to this as the Kozai effect or the Kozai-Lidov effect from the Japanese scientist Kozai and Russian Lidov. But it's now clear that von Seipel was the first to discover the effect in question. So with this word, I will close this opening address. And again, wish you welcome to Stockholm, and I hope for a fruitful and interesting meeting.
Thank you, Göran, and welcome to all of you. We are here representatives of what one could call the Oort cloud community. And I look forward to 2 days of fruitful and productive discussions and so on. Okay, but there is one word I want to focus on, and that is contacts. Because we in our community, we have participated in several meetings before, big meetings, where the Oort cloud has figured among the topics, but together with many other things. And I guess that this meeting is special because, to my knowledge, this is the first international meeting devoted to the Oort cloud. And this gives us a special chance to form new contacts. I mean, many of us know each other since ages, since decades before. But for instance, I do not know all of you, and I don't think anyone here knows everybody. So we are here at a place and a time to make new contacts. I can see before me that there's a chance of new ideas being brought to new people during the discussions at the posters or coffee breaks or whatever. And that is going to be quite important, I think. New ideas, new ways of cross-fertilization that may lead to new projects and perhaps major discoveries in the future. Well, we don't know, but this is one thing that one could even hope for. So, so welcome again, and let's have 2 days of really nice and productive discussions. Thank you. So we can start the morning session, and Hal Levison is our chairman.
I am. Well, welcome. I want to first of all start off by thanking Hans and the organizers of this meeting. It really is great to be able to have a meeting dedicated directly to the Oort cloud, which, as many of you know, I've been working on since I first got into planetary science a long time ago. You know, Hans is right. I met a good fraction of the people in this room in one meeting in 1992, right? And I'm going to get those rights. Remember that meeting? Well, these 3 guys were there, so it was great. We've known and working on this ever since. So let me start off with introducing Alessandro Morbidelli to talk about the origin of the Oort cloud.
All right, so thank you very much, Hans, for the invitation. It's a big honor I feel home here because, you know, Trump may have a tower in New York, but they have a Morbi Centrum here. So this is really an introductory talk, and probably most of what I will tell is known to everybody. But at the end, there will be some new results. But okay, really an introductory talk. So because it's an introductory talk, I decided to start with this slide, this picture, artistic view of the scattered disk and the Oort cloud, because it looks nice, but it's wrong. And why is it wrong? You have 5 seconds to answer. Because in the Oort cloud, comets are very eccentric, so there is actually no hole here, right? Comets can, this is a correct representation in semi-major axis versus inclination, but not in physical space, because comets are very eccentric, and so there is no hole in the solar system. I also realized flying here that in Sweden, there is the biggest representation of the solar system to scale. So the sun is actually close to Stockholm, or in Stockholm, is the second biggest half hemispherical building in the world. And that sets the scale. And it's a scale 1 in 20 millions. And it's very convenient because the heliopause falls, well, wow, this is difficult to direct, it falls just up there at the border of Lapland. Okay. But if you wonder where is the Oort cloud in this solar system, and you know the Oort cloud is centered around 20,000 AU, that would be halfway between the distance of Stockholm and the moon. And the moon would be in the outer Oort cloud, barely bound. Okay. So the Oort cloud is really far away. And okay, so how did the idea of the Oort cloud came up? By Oort. It came up by looking at a diagram like this, showing semi-major axis and inclination of comets, realizing this difference between elliptic comets with a period of less than 20 years and the more isotropic comets with period longer than 20 years. But Oort in particular realized that there is a pile up of comets with a semi-major axis of the order of 10,000 AU, which means that their binding energy is of the order of 10 to minus 4. And this is strange because every time a comet penetrates into the inner solar system, so through the giant planet region, its energy changes randomly by a quantity which is of the order of 10 to minus 3. Not because of encounters with the planets, because they may miss all the planets, just because of the motion of the barycenter of the sun around the barycenter of the solar system, which is displaced by 10 to minus 3, which is the mass of Jupiter relative to the sun. So in order to see all these comets with a binding energy of 10 to minus 4, it means that these comets are coming into the inner solar system for the first time. These are new comets. And these are new comets. There must be a reservoir there at 10,000 AU. And this is how the idea of the cloud came up. So the cloud is called the cloud because it's isotropic, and you may say, okay, it's isotropic because we have all possible inclinations. But of course, having a random or uniform distribution of inclination does not mean that the distribution is isotropic. You could have a cigar like that. Right? So the cloudy structure of the cloud comes from the fact that not only the inclinations are uniform, but also the argument of perihelion and the longitude of the nodes are uniformly distributed. And that sets the geometry of the cloud to be a sort of sphere, to be a sort of cloud. So how could the Oort cloud form? Clearly, comets could not form at 10,000 AU. The material, first, now we know disks are not as big, and anyway, the material would be too dispersed to form any kind of object. So objects have to be placed there. And so the investigations of how the Oort cloud could have formed started in the middle of the 20th century. Here I quote 2 historical papers. I think Duncan, Quinn, and Tremaine have been the first to do some serious simulations of Oort cloud formation. Of course, with the tools of the time, they couldn't do a complete simulation from the beginning to the end. So they combined the Monte Carlo approach with direct integrations. And for the direct integrations, they started from objects which were already on extremely eccentric orbits with an eccentricity of 0.99 and the sun major axis of 2000 AU. So it's just the last stage of formation of the Oort cloud. Then, of course, technology evolved, and in 2004, the problem has been done, I think, for the first time completely using direct numerical integrations and starting from an actual disk, so a population of objects in the giant planet region from 5 to 40 AU, 0 eccentricity, 0 inclinations. To work to form an Oort cloud, you need the giant planets to scatter objects, you need the galactic tide, you need passing stars, and this work was developed accounting for the current galactic environment. We will talk about clusters later, in the post-gas phase, so there is no gas drag issues in this simulation, and also at the time in 2004, we still thought the planets formed on their current orbits, and so no planet immigration or planet instability was featured in these simulations. So how does the Oort cloud form? Before showing the actual animation from the simulations, just a scheme to show what we are talking about. The Oort cloud forms because the plane of the solar system is actually very inclined with respect to the galactic plane. There is an inclination of 60 degrees, actually 120 degrees. The solar system is retrograde with respect to the galaxy. And so when the planets scatter objects out, so the objects are scattered on eccentric orbits, which keep an inclination relatively small, between 20-30 degrees. So these bodies go out with a very high inclination relative to the galactic plane and an argument of perihelion close to 90 degrees due to this geometry. Okay. And then, because of the material of the galaxy distributed on the galactic plane, these bodies undergo the Kozai-von Zeipel effect that was mentioned before. So that means that when a comet goes out, it has it's of course coupled to the planet. So say for instance, has a perihelion on 20 AU, and when it goes out and starts to see the potential of the galactic plane, the argument of perihelion is around 90 degrees. So it's at sort of the bottom of this cycle. And then the Kozai effect increases the inclination relative to the galactic plane, decreases the eccentricity, and therefore increases the perihelion distance. So the body goes up in perihelion and decouples itself from the giant planets, and it's trapped in the Oort cloud. It's not scattered by the planets anymore. So coming back to our scheme, as the body goes up, because of the galactic plane effect, the inclination with respect to the galactic plane increases, the eccentricity decreases, so the perihelion increases, and the body is captured in the Oort cloud. At this point, the orbit starts to precess around the galactic pole, and the precession around the galactic pole can turn a prograde orbit with respect to the Sun into a retrograde orbit. And this is how the inclination of the Oort cloud gets randomized. With this in mind, we can see these nice animations taken from the simulations presented in Downs et al. 2004. I actually don't remember who did this animation. It was me with their data, or Hal or Luke, I don't remember, too long ago. So what are we seeing here? We are seeing the initial conditions, so particles distributed in the giant planet region from Jupiter to slightly beyond Neptune, and they are color-coded with respect to their initial semi-major axis, and we see their evolution in respect to semi-major axis and perihelion distance, and the time is here at the top. So we can start, and what we see is that under the effect of the scattering of the giant planets, a scatter disk forms, which is this structure here, all semi-major axis, but perihelion in the giant planet region. And when bodies go beyond, say, 10,000 AU, then they start to feel the galactic potential, and that's why their Q rises for the reason I explained before, and these bodies decouple from the giant planet and cannot be scattered anymore. So at the same time, we have the formation of the scatter disk that we observe easily, and the Oort cloud, which is here, that we cannot observe because the perihelion are too far away, but it is deduced from the flux of new comets, as Oort did. If we want to look in terms of inclination, so this is the same movie, but showing semi-major axis versus inclination, then the bodies go out, and in the scatter disk, the inclinations are moderate, within 20, 30, 40 degrees. But again, when the galactic tide kicks in, because of this combined precession around the galactic pole and the galactic and the pole of the solar system, then you randomize the inclination distribution. So this is the classic view of how the Oort cloud forms. It forms between about 10,000 AU, 100,000 AU in the current galactic environment, if you want to have an Oort cloud at this location where the new long period comets come from. An important point to be made is that this works if you have no gas in the system. And this paper in 2007, led by Ramon Brasser and with Martin Duncan and Hal Levison, made this point very clearly. So they used a standard disk, minimum mass solar nebula model. So I put here the parameter, truncated at 100 AU, so it's not going very, very far away, and also decaying in time with a median, with a characteristic time of 2 million years. And they redid the Dons et al. Simulations. And what they showed is that if a comet is small, so with a radius, say, of 1.7 kilometers, so this is already 3.5 kilometers in diameter, you see comets do not reach the Oort cloud at all, because as soon as they are scattered, the gas drag recircularizes their orbit. And you could think, well, if the comet is scattered in the vertical direction, it goes out of the disk, but still, the disk has a given thickness. At the node, the comet has to go through the disk, and so circularization is very effective. You have to have sizable comets, 5 kilometers in radius, to start to see a few reaching the Oort cloud. But this would be a very anemic Oort cloud, certainly not capable of sustaining the flux of new comets that we see. And you start to form a significant Oort cloud for comets of 30 kilometers in radius. So these are big guys. Some are so big, right? For the comet Berardinelli is bigger than that. But most of the new comets that we see are actually small, are about 1 kilometer in size, in diameter. And so they fall in this regime. So this shows that because the Oort cloud is made by a lot of small comets, that when the classic Oort cloud formed, the gas should have been already removed. At the time, this was a bit surprising because people think that these comets are ejected from the giant planet regions as the planets are growing. But the giant planets are growing in the presence of gas, so there is gas there. But in more or less the same years, it was realized that during the gas disk phase, the giant planets cannot have the current orbits because planet migration brings them in a compact resonant chain, and that the transformation of the orbits of the giant planets from the initial orbits that they had in the disk to the current orbit happens through a phase of giant planet instability once the gas is removed. So this is what is called the NIS model. This shows a representation. So the planets stay in resonance for a while, but they interact with the trans-Neptunian disk. At the end of the gas disk phase, the only planetesimals that survive are beyond Neptune, because those in the giant planet region has been consumed during giant planet growth. And after a while, which in this movie is long, but we think now it's just a few tens of millions of years maybe, the planets become unstable and they disperse this disk. And so this disk is actually dispersed after gas removal, and so there are no gas drag problems, and so the Oort cloud can form. Recently, in 2017, a work led by David Nesvorny explored the formation of the Oort cloud in the framework of the giant planet instability. And this plot here shows the final distribution of the bodies. So in a simulation of the giant planet instability, like the one that I showed, but together with the current galactic environment to see the effect of the galaxy on the scattered bodies. And you see again a scattered disk, and you see the Oort cloud. This is 7 major axis eccentricity or 7 major axis and inclination. The results are very good. So the scattered disk today comprises 3.3% of the objects initially in the original trans-Neptunian disk. And the Oort cloud, at least beyond 1,000 AU, comprises 6.5% of the bodies, about half within 20,000 AU and half beyond 20,000 AU. These distributions here produce fluxes of short period comets and long period comets that are very consistent with what is observed in terms of flux, number fluxes, but also orbital distribution of the comets. And indeed, the population ratio between the Oort cloud and the scattered disk in this simulation is about 20, which is consistent with the ratio that is deduced from the fluxes of JFC, Jupiter family comets, and long period comets, which is about 44 with a big error bar, because the biggest problem is to compute the actual physical size of comets from their activity, on which there is a big uncertainty. So apparently there is no need for exotic sources of the Oort cloud, like capturing comets from other stars, which is possible. The dynamical channel is there, but we don't see actually the need for a massive capture of comets from elsewhere, because the trans-Neptunian disk dispersed during the giant planet instability can make a massive enough Oort cloud, which was not believed 10 years, not understood 10 years ago. Note, however, that this diagram seems to reproduce everything except the bodies like Sedna or VP113, which are not really in the Oort cloud, but still they have a quite large perihelion, so they are very decoupled from Neptune. And it's always often said that these bodies probe the inner Oort cloud or the Hill cloud. So how can we unform the Oort cloud, the Hill cloud? I think this will be discussed in the talks later, but I will say something briefly here. So clearly, if you want to decouple objects closer to the sun, you need a heavier and more massive galactic environment. So you need to do it when the sun is still in a stellar cluster. Again, Brasser and collaborator in 2006 did the simulations using various potentials for a cluster model. You always use the Plummer potential, but they change the density. And they see that if the cluster is very weak, then we get the classic results with a scattered disk and an Oort cloud, and these decoupled objects like Sedna, CR105, and so on are not reproduced. But if you have a massive enough cluster, you can start to decouple objects between 100 and 1,000 AU. And so you can start to reproduce Sedna and so on. And if you have a very massive cluster, you can even reproduce CR105. However, note that if you have a cluster and you produce the inner Oort cloud, you don't produce the outer Oort cloud, because the outer Oort cloud is simply unbound. The cluster is too heavily populated. So the question is, how can you have both an inner Oort cloud and an outer Oort cloud at the same time? And I think this is a problem. So that's why I put this saying that you can't have your cake and eat it too, because either you do the inner Oort cloud and you fail making the classic Oort cloud, or you make the outer Oort cloud and you fail making the inner Oort cloud. So how could it work? So during the giant planet instability, the sun must have been out of the cluster, because otherwise the classic Oort cloud would not have formed. So the inner Oort cloud must have formed before. The inner Oort cloud probably formed before from the planetesimals that were in the giant planet region, and have been scattered as the giant planets were growing. But as the giant planets were growing, there was gas. So at face value, we would expect that the inner Oort cloud does not contain comet-sized bodies because of gas drag, and contains only big bodies like Sedna and its companions that we see. So this is actually a bold prediction that should somehow be verified, and probably the only way to verify it is by using occultation. And in the past, James Alcock had even proposed a space mission, WIPOL, in order to probe the inner Oort cloud size distribution using occultation. It has never been done, but I think it would be a very interesting mission to do. However, there are two possibilities to make an inner Oort cloud containing small objects as well. One is to play on the timing of the dispersal of the cluster and the giant planet instability. You could imagine that the giant planet instability happens just as the sun is coming out of the cluster, so that the first objects scattered fill the cluster, those which are scattered a little bit later don't fill the cluster. For me, it's a very contrived timing, but I know that Hans' group is working on this, so we'll hear more probably about this in this meeting. We will see. The other possibility, and this is a new result, is that Planet 9 is out there. I don't know if it is out there or not. There are several indications, some in favor, some not in favor, so waiting for LSST to say what's really going on. But let's assume for a moment that Planet 9 is there. So where would Planet 9 come from? Planet 9 would be ejected during giant planet formation and during the cluster phase. There is actually a paper just came out by Isidoro, myself, Sean Raymond, and others in Nature Astronomy last week. And so this is an animation taken from that work. So we envision that when the giant planets were forming, Jupiter and Saturn formed first. Beyond Jupiter and Saturn, there were a bunch of super Earths of, say, 5-6 Earth masses that were trying to migrate, and they collide with each other and eject each other, and they form Uranus and Neptune with some planets ejected. If there is a cluster, so not only you form Uranus and Neptune beyond Jupiter and Saturn, but some objects are ejected, and because we are in a cluster, they can be trapped in the inner Oort cloud, say close to 1,000 AU, on an eccentricity. Oops, disappear my planet. Why it disappeared? It's there. It did not disappear.
How fitting!
Okay. There has been a problem in the movie, but it's there. So in animation is there. I don't know if it's there in the solar system. In animation is there. So okay. So once you have a planet there, then the gas goes away, and then the giant planet instability occurs in a gas-free environment. But now the giant planet instability occurs with the planet in place. So this is the planet captured in the previous animation that is still there. And these are the snapshots of where the comets go. Okay. And so the comets start to be scattered from this trans-Neptunian region, form a massive scatter disk, then the scatter disk starts to decouple in the classic Oort cloud because of the galactic potential, but they start also to decouple at the planet 9 location because of the torque of planet 9. And so you form both a classic Oort cloud and an inner Oort cloud centered on P9. And P9 is being trapped by a cluster, so this is really an inner Oort cloud where a cluster would have placed it, even if the cluster is no longer there. Okay. So this is the possibility that I see to have an inner Oort cloud populated of small comets, because it reminds where the cluster was because of the trapping of planet 9, but there is no more gas, so there is no gas drag obstacle there.
How massive is this?
Sorry?
How massive is the planet?
5 Earth masses.
And what fraction of the planets you start with get trapped?
It's a good question. It's in the paper by De Souza et al. I think you asked me a difficult question. I think 30% of the Oort cloud mass, something like that, it goes in the inner Oort cloud.
No. I mean, of the planets you originally start with, what fraction of those?
Oh, the planets. Okay. So for each planet ejected, the probability to be trapped is 10 to 15%. And typically in the simulations of formation of Uranus and Neptune, it's a model, so we eject 2-3 planets. So the overall probability is of the order of 30 to 40%. Okay, so these are the final distributions in the simulation. So without planet 9, so the classic Oort cloud formation in a gas-free environment, which, as I said, do not reproduce neither Sedna nor VP 113. And this is what happens if you just add planet 9 pre-captured during the giant planet formation and the cluster phase. Now, it's a very different portrait, but unfortunately, it's very difficult to say which is the correct distribution. From the point of view of the fluxes of Jupiter family comets and long period comets, this distribution and this distribution give quasi-identical results. So it's very difficult to discriminate between the two just by looking at comets. And so one should really probe somehow the size distribution in the inner Oort cloud, as I said, and occultation seems to be the only way to do it. So on that, I will conclude. So I would say that the formation of the classic Oort cloud is well understood. And it's clear that the Oort cloud should have formed after the removal of the gas from the system, because gas drag would have prevented the comets to go in the Oort cloud. Big objects, no problem, but the comets could not go there, and we see comets coming from, small comets coming from the Oort cloud. So the phase of giant planet instability is perfect for that, because it occurs by definition after the removal of gas, when the planets can break their resonance chain. So in this phase, new simulations by Nesborn et al. Show that we can produce both at the same time both a scatter disk and an Oort cloud, so it's the same objects from the physical point of view, and these structures, scatter disk and Oort cloud, are consistent with the observations of Jupiter family comets and long period comets. The inner Oort cloud instead is poorly constrained observationally. We know there are big objects there, we don't know about small objects. It definitely should have formed during a stellar cluster phase, The stellar cluster phase should have been earlier, and in principle with some gas still in the solar system. So it should not have small objects, only big objects, unless we have this perfect timing in between a dispersal of the cluster and the giant planet instability that I'm not very convinced about, but to be studied, or that planet 9 is there and was implanted in the inner Oort cloud during the giant planet formation phase and the cluster phase. And then once it's there, it can hijack bodies that are scattered during the giant planet instability and trap some in the inner Oort cloud on their way to the outer Oort cloud. So, thank you very much.
So we can take some questions. We have a few minutes, but I have 2 comments. Since I'm the chair, I would take the prerogative.
Comments or comments?
Comments. The first is that I want to emphasize the role of passing stars in the formation of the Oort cloud, right? But galactic tides are what remove the comets from planet-crossing orbits. But in order to get the mixing that we see, in order to get the inclination distribution to make the Oort cloud long-lived, you need passing stars in order to kick things and mix things up.
Yeah.
That's one thing I wanted
That's
to
very true, because this Kozai effect puts all the comets in some sort of cone in phase space, which is also the lost cone to produce the long period comets later. So you need the passing stars to extract the bodies from this cone, so that they are happy to live for 4 billion years, and put them back in the lost cone in the time of injection. This is perfectly true. I didn't mention that.
So I wanted to emphasize that. The second, I will point out that you could solve this timing problem by having the outer Oort cloud captured from other stars.
That's also true in that case, yeah.
So there is another mechanism to do that, right?
Because if you do the full instability in a cluster phase, so you produce only the inner Oort cloud, and then you have to capture the Oort cloud from another source.
Yes. I'm not advocating that.
No, it's true.
I just wanted to point out.
No, it's true. It's a possibility.
Yes, go ahead.
In your initial discussion about the isotropization of the inclinations, you emphasized inclinations, but I really think that the emphasis should be on the latitude of perihelion, because just as your figure was showing, if you turn a comet like that, but it's still in the low latitude, and for that I think
the passage of stars randomize the distribution a lot. Yes, sure.
Can't do
absolutely.
Yes, I have a comment about the second point. That I think that the time scales for the gas dissipation in the planetary disk and the time scale for scattering of bodies are different, and the time scale for the scattering bodies is longer, and therefore the gas drag has very little effect on the dynamics of the scattering of the bodies that are scattered.
I'm not so convinced, because the scattering occurs as soon as the planet reaches and destabilizes the object, so the planets are growing, and then the scattering occurs on the orbital time scale. So I would say the scattering is shorter.
The aerodynamic drag occurs on a very short time scale.
Yeah.
And the one thing, Julio, that we found is that you circularize the comet at the angular momentum after it gets scattered. So these things are all further away, and so they actually become decoupled from the planets and never come back in.
You create a gap in the planetesimal distribution. The planetesimals leave the giant planet region and park beyond Neptune and stay there, waiting for the giant planet, post-gas giant planet instability to happen. So actually this material that was in the giant planet region can be in the Oort cloud today through these two-step mechanisms. So these planetesimals are scattered, some can enter into the asteroid belt, the C-type asteroids, then CCC dichotomy, this stuff like that, but most of them are actually scattered out, they are circularized beyond Neptune, stored with the rest of the trans-Neptunian disk and then dispersed later during the giant planet instability. So I think we do sample the giant planet region in the Oort cloud and the scattered disk through this two-step process for small objects, not for big objects.
Assuming the Oort cloud wasn't captured.
Yes. Price.
Hello, could you go to the plot where you show the semi-major axis first inclination distribution of all the inner and outer Oort cloud objects?
You mean in the simulation? Or
Yes.
you mean this one?
Yes.
Okay.
So why is it that we see like this sort of like a truncation between the inclination distribution for inner Oort cloud objects, and it's much more isotropic, but in between the two there is kind of like looks like a trough.
Yeah, exactly, because this is a region that is too bounded to the sun for the galactic tide to be effective, and too beyond the Planet 9 for Planet 9 to be effective. So the fraction of the population trapped in this intermediate region is actually much less than that trapped in the Oort cloud or in the Hill cloud.
Are these test particle cases?
Yes. Yes, yes.
I should talk about that.
Colin?
You
are the chairman, not me.
That's all right. So the difference between the two models, apart from the size distribution, is that the Planet 9 version implants the things in the inner Oort cloud later than
yes,
the
exactly.
version.
Exactly. So when you implant Planet 9, you may have also implanted other big objects that are immune from gas drag, but not the comet-size objects. But when the giant planet instability occurs, there is no gas, and these objects are just trapped there because of the torque from Planet 9. So these can be objects of any size, including sub-kilometer objects.
I wonder whether or not there could be any difference in them because of the slightly longer time they spend in the inner system before being ejected in this model. Just to try and think of other ways that there might be some observational tests, but I guess it's not significantly longer if it's during giant planet instability.
Also depends also on when the giant planet instability occurs, which is now thought to be a few tens of millions of years at most, so probably not.
It's not that long, yeah.
By the way, there's no evidence that this population exists.
Sure, no, there is no evidence. There is no evidence that it doesn't exist either, because we don't know anything about small bodies. So that's why I'm saying that a mission like Whipple, that has been sort of forgotten, I don't see it in the decadal survey, for instance, would be extremely useful to understand the outer solar system.
No, I agree. All right, we have to move on. Keep on schedule. Okay. See, I am doing my job.
There you go.
Our next speaker will be made Schwamb, the origin of the Sedna region.
Okay, see if that works. So I lied. So knowing that Morby was going to talk, I thought he was going to do the setup for me, which he did. So I thought I would step back a little bit and as an observer, talk a little bit about how we've sort of looked at the Sedna region, where it was in the past, where it is right now, and then the future. Because basically by the end of the year, everything will basically change, I think, in terms of perspective of the outer solar system. And so short answer, LSST. But I think I thought it would be good to sort of give that context, especially because there was a really great intro from Morby about these different, about the sort of models and what we think we know. So taking this step back as an observer, right, what has always been weird about Sedna, sort of leading the way from, Mike Brown, Ted Trujillo, and David Rabinowitz, was that, again, this thing of it's completely detached from the planetary region in the sense, right, of it having both that perihelion so far away from Neptune, but also the aphelion being too far away. And again, I guess it still comes down to that initial thing of what is that impulse that took it off of the orbit that was allowing it to be sort of coupled to the planetary region, right, where those giant planets are, right, and what impulse gave it to come out. And I think, again, that's still, I think, a question that seems very open. I'm less optimistic that Planet 9 exists. But even if it is Planet 9, right, there's a lot more details I think we need to do to potentially get there. And a lot of the models people are trying to propose that may get us there. Right, and so I think, again, for me, the really still interesting thing, and Morby showed the great animation, right, of showing really that Sedna and Sedna-like objects, can we not call them Sednoids? Because Plutoids are big objects in the Kuiper belt, so people have started to call these things Sednoids. That would be big things like Sedna. Let's just call them the inner Oort cloud or Sedna-like objects, Sedna region, something like that. So for Sedna-like objects or the Sedna region, right, we're basically, these things are just too far away from the edge of the solar system to feel the effects of passing stars and galactic tides. As Hal mentioned, both of those things are important, right? And so again, it's that no man's land of these objects and where they are. And I think today we're still just at the tip of understanding how many objects are there and what is that orbital distribution. So I pulled this up for my thesis presentation because I thought it was good to show the past a little bit, which was that I was like, look, there's so many different methods. Rogue Planet, although it's not necessarily going to produce objects that are on those orbits, it's basically, is there, could be planet. If it was doing something more uniform, little did we know. Stellar flyby, right, cluster birth, and interstellar capture, right? And so the idea being, I think, is that we thought that there were more avenues. And I think some of these are still viable today and have been put into new sort of remixes. But one of the things was that heavily sort of looked at was trying to figure out observationally what we could say. And I think one of the surveys that kind of looked over a wide area of sky was the survey I did with my ground and my thesis, looking about 12,000 square degrees, within plus or minus 30 degrees of the ecliptic, looking for new Sednas, using the Samuel Ocean Smith, and again, trying to use sort of, the biggest camera that was stuck on there, the Quest camera at the time. I came up with nothing. We redetected Sedna and found nothing. Everything else was happily scattered disk object or anything else than normal sets of objects. So again, just sort of showing that with the semi-major, the perihelion distances here, right? Everything was happily in there. This object was the one we were waiting for a while. It turned out to be a scattered disk object. And on the observation side, we got to wait that 1 year from discovery to figure out which one it is, which is quite painful. And I think there's no way, unfortunately, around it, even with LSST, because these objects look the same pretty much if they're at perihelion or aphelion at discovery. And so we really need to wait the year to break that degeneracy. So I think, again, on the observer side, even when we start detecting objects, again, point here is LSST, we're still going to have to wait a bit to get orbits nailed at with 1 year arcs to be able to start really seeing, unless it's really far out, then maybe we'd be able to differentiate easily. But whether it's actually an object aphelion, perihelion is still something that's frustrating as an observer once you find it. You know its heliocentric distance well, but you don't know which orbit it's on. So out of these models, right, one of the things that I think was nailed before we got into finding the next Sedna-like object, right, or really the third object, maybe you might argue, was that looking at this cluster birth, because that had, as was shown by Morby, had really good predictions for what the orbital distribution would look like. That could be tested, had sort of clear differences that you could tune a parameter and easily get some differences. And I just want to highlight, because I like this from scale, is that this is thinking about shoving our, Oort cloud on there. And this is, again, a core of an embedded cluster, right? And there's Sedna's orbit for scale of just how many stars are packed in, right? So you can see in the optical, and here we go in the near infrared. Just appreciate the scale, right, here for how many stars actually could come by, right, an embedded cluster if you're near that core. So again, I think that's something of clearly if the sun was born in an embedded cluster, and most stars are, you come out of this, within, 20 million years or so, that you're again, right, it could be a small part of the history of the solar system, but it may only still be locked in that, region with Sedna. So I think it is still important to understand what the impacts are, particularly even if the hot model right now still is Planet 9. And so I just appreciate this fact that, again, if the sun was born in a embedded cluster, there were lots of stars coming by. But maybe it is still true that it might be the last stellar encounter that had maybe the most influence right before the sun left the cluster. And just to give you that, right, again, just to give you the scale, right, it always blows my mind, right, that half the distance to Alpha Centauri, right, is, again, the size of the green that we have on there, the size of our Oort cloud, roughly. So again, this plot has been shown to you before. So this is showing Brazer et al.'s 2006 different distributions for basically the inner Oort cloud population. Here the colored dots are showing the different objects. We have Sedna sitting out right there. And the idea being is that if I took my survey observations of only redetecting Sedna, although SED is still useful because we know what we didn't find. We didn't find any other objects. Basically, if you put your distribution up and say that those triangles basically are your population, I could say which ones I could rule out. And the only one, assuming a reasonable size distribution or brightness distribution, absolute magnitude distribution, was the 10 to the 3, the sort of weakest cluster. That everything else basically is fine because Sedna is at the tip of this population. And if there was more, basically if you had anything else that was closer in, right, then you would start to get heavily, more massive cluster in the sense that you would get a population where Sedna was in the middle of that distribution. Then you'd have problems because on the bright end, my survey went to 21.5. We should have seen those objects. And we didn't, right? So there's not a massive, huge number of objects sitting out at 21 or 21.5, right, out at 80, 90, 100 AU that we've missed. In my survey with pan-stars, we're pretty confident in that. And I think it's one of the reasons why some of this is stagnated in some sense, because we had to get very much deeper to sort of get to the next object. And just to highlight again, Ramon did this again using a slightly different potential, and we got the same answer. As long as Sedna is sort of the leading edge of this population, everyone's happy. It's copacetic with what we knew at the time, right, for wide field surveys that went to 21, 21.5. So it took to 2012, which made me feel better, graduating in 2010, that it took a while to get the next object. And again, that took having Subaru to get you there. And so, now there's 2, right? You can do lots more with it, right? But it's still, again, right, I think we're still in the small number statistics game, and that's some of the problem that's going on. So you have 2012 EP113, as was highlighted, again, from Shepard and Trujillo, sort of, and again, a few others have now sort of fully been linked in. And again, I know there's some objects that are on the edge of being in the center region, but really you might argue this is going from, from Pluto to sort of the discovery in the, of the QB102 right here, 2012 EP113, sort of being that next leap. And again, that's the argument now with more objects, right? That's come in both from Bagatine and Brown, as well as Trujillo and Shepard, of there being that their path needs to be a 9th planet, with really the model here being that there is weird clustering going on in multiple angles in orbital space. I'm not sure I believe that, although there's a lot of papers that say that may be true, because again, I'm worried we're in small numbers in some ways, and that also there's no wide field survey that's covered a lot of sky looking for these, because to get to this, we really need to go to 24th, 25th magnitude to start finding these things. Again, right, because this has been the lull basically for a while. And again, if you've noticed, there haven't been many discovery papers or survey papers that have come out recently sort of in this region after the sort of discovery of a few more of these objects in sort of the canonical Planet 9. So we're still sort of waiting, I think, for the next leap in sort of getting detections in the Oort cloud. But if you do believe this model is true, right, the argument being it's the shepherd dog shepherding your sheep, right, to put objects onto specific orbits, right, or alignments in multiple ways that have been in a series of papers by Bagatine, Brown, and others. So the argument is that it's somewhere likely located in the galactic plane in the north, which makes everyone happy because that's where everyone has avoided, even me, because we have to do difference imaging and we make people that do supernova deal with that. So it is an area that no one's really looked at in the north, in the galactic plane, right, is probably an area that's fairly unexplored. And you can see that if you look at the minor planet detections, like it drops significantly in the heart of the galactic plane. And so that is, the current best estimates with the Zwicky Transit Facility, Pan-STARRS, Dark Energy Survey, right, is that Planet 9, if it's there, is in here. Could be somewhere, and could be 21st magnitude, 22nd magnitude likely, and so easily observable, but it's because we haven't been looking. So there's an observational test there. But I want to highlight, again, I think there have been other models. It's not maybe time to get rid of them, because I like this plot by J.P. Cavallars, where he talks about, right, just taking the detections or what was posed as being part of maybe orbits that were aligned or influenced by Planet 9, just saying, look, that if you look at using a survey simulator about detectability, the blue being a higher probability, white being less, the things that you find aligned tend to be the things that you're more likely to find. And so again, I think there's a lot of things about disentangling the biases that we have to worry about as observers to help our theorists and dynamicists be able to test the models. And so I think this is some of what I think the debate at Planet 9 is how you choose your statistics, how you choose the objects you're going to use, and then how you interpret it. So again, this Corey Shankman does the same thing with the ASA survey, so the Outer Solar System Origin Survey, where they do have a really high detection efficiency. They've tracked all their objects, and they have a survey simulator, and they find no signature of Planet 9. Now, on the flip side, it has been also redone in a different analysis, and Brown and Bragantine claim that there is basically there is a signature. It's just that ASAS, because it only looked at small regions on the sky to get to its 800 TNOs, it used CFHT, so it was using a 4 meter. You can't get all the time in the world, so they just happened to not look where things would be influenced by Planet 9. So of course they don't see anything. And so I think the debate continues, although papers continue about whether or not we see things. So I think where are we today? There's lots of objects that are being argued one way or the other of telling you that there's Planet 9, right? But I think maybe for observationalists and even in the room for people who are on some of those papers just said, it's not clear it's real. So it's nice to see that there's still some doubt today. And I would happily like to be proved wrong. So one of the things that I think is important and I would love the answer to is where do we actually start calling the inner Oort cloud and where do we start calling the Oort cloud? And where do we say that this is the Kuiper Belt Trans-Newtonian region and that things are clearly separated? Because in 2015, sort of when BP came out, when it was discovered, right, we were like, okay, which objects should be counting as Sedna-like things that you should be then looking at and comparing when you do all of these orientation statistics? And so the argument from Ramon was that he shoved as many particles as he could into the numerical integrator and looked at how far you could push things and all the dynamical interconnected highways within the scattered disk. And so what we came up with was sort of these different regions that you have your resonant fingers. So again, we have something major axis versus perihelion that basically you can go hog wild, right? Shoving things and changing perihelion, right? Basically, if you have enough particles to explore the parameter space at the high, right? And so, but those things are all in some way, again, tied to the planetary region. These are, again, things that are in cosi, they're in main-mutation resonances, that's what's pushing it. So if you're in that region, right, the blue box, you're probably not a Sedna-like thing, you're not really detached. And then the argument is that all these things down here, that below, 45 or 43, perihelion distance, even going out to 900 AU, you can still be linked to the Neptune. Because this was all just done with shoving things into the scattered disk and letting it run. So with a reasonable model for Neptune migration. So the argument here, I think, is that, well, again, people start pulling things at a Q of 40. And my argument is that true? And so I'd love more clarity, especially as we're going to head into more detections. Where's the differentiation between these? So when as observers should we be doing our statistics with things that we actually know are Sedna-like objects and maybe not? And maybe it is messy, but I don't know what the right thing to do on this is. And so my argument is that this would be the plot that I would use at the time and say, those are the objects to choose. But other people have gone to much lower perihelion distances. And so I think when you do that, you get different answers. And so I'm much more conservative on this. And so the question I have for everyone in the room is, where are these differentiations? Where are these delineations? Can we make them? And how does that help us, especially as we're going to get answers to these things soon? So, right, observers should be looking here is my argument, but that might not be everyone's opinion. What I want to sort of change and sort of highlight is, and maybe be the cheerleader and be excited about is, this all changes basically next year. And it is coming online right now. So it is expected to start the Legacy Survey of Space and Time in about November. So the first look, where the image is supposed to come out, I think, in some press event on June 23rd. But why LSST is amazing is because when people are interested in astrophysical transients, the solar system therefore becomes their verbin. And so it's one of the 4 science drivers because the dark energy people and the supernova people needed us. And so we have as much power to leverage the survey and get the observing cadence to be as good as we can, modulo we have to let those other people do their science. Maybe not, but we let them do a little bit. One of my jobs as co-chair of the Solar System Science Collaboration is to push back on all of their requests, and so we've done pretty well in trying to optimize the survey. And so this is going to be a 10-year survey. We're not going to be scrambling around to be like trying to get in orbit. We're not going to be scrambling around because we're going to lose an object. And so really to highlight that everything literally changes next year because of the sheer amount of data that's coming in, right? So this is going down to 24.5 limiting magnitude. It's observing in UGRIZ filters, though U and Y are less important for outer solar system. We get no detections, but it's hundreds of visits per object. These numbers are the ones I can show you because the press release is now embargoed. So, but I can tell you the number, but don't tweet it, is that we now, using a survey simulator built for the LSST, actually have numbers for these. And so it is roughly 40,000 from the old numbers, but we can actually say it's about 38,000 with the latest models for the Kuiper Belt and transit-tuning region that LSST will find. The more exciting thing is that we get those in the first 2 years. We get 70% of those detections. So those papers are coming out on arXiv tonight, so you can look at those. But the idea is we can actually tell you that in the first 2 years of the LSST, we're going to completely transform our view of the outer solar system. And the reason why, right, is that we know about 5,000 TNOs today. So imagine going to 38, 40,000 TNOs, plus all the things for interstellar objects. So I just want to highlight this has been something on my nightmare of helping to advocate and make sure we get to the right cadence. But this is basically the number of visits over the 10 years. There's deep drilling fields where they're going multiple observations just to go deep for galaxy things. Most of those are not useful for us, but there is cosmos up here by the ecliptic. The really important thing is the northern ecliptic spur, which we have fought to keep as a community. And that's where Planet 9 is. That's also where part of the alignment is, right, for the inner Oort cloud objects. And so we're going to have one survey that covers all of that sky, right, both sides of the ecliptic, 224.5, over a decade. Most of these detections are coming in the first 2 years, right? So we're going to know what the outer solar system looks like, particularly, and we're going to be diving into that region. And so that's, I think, the message I want to get is that everything you're thinking about, think about how we test it with this, because we have a survey simulator that can be used to test your predictions, but also these things are going to be coming in live. So what should we be looking for? What we should be following up? And what do you do when you have, 30,000 TNOs? What signature should we be seeing for these different populations? And that's why I ask, how should we be dividing these things up? So again, we talked about Planet 9, so let me highlight that. So slightly different sort of observing cadence, and this was before the latest baseline, but in 2023, we were advocating for, getting what we wanted on sky, and just to highlight, this was where the latest was for Planet 9. It's the whole distribution, but we know we're up there. And again, just to say, it's sitting in that NES. So Planet 9 is going to be found if it's literally there, and it's the prediction that Bound and Bragantine are saying, because it should be easily visible in the images, and Rubin Observatory is going to be doing perfection in terms of image attraction because the transient people need it. So for free, we don't have to do anything. This is going to come for us. And to highlight even more for free is that Mary Yurch at University of Washington has been tasked with building the moving object pipeline to go all the way from intravenous objects out to about 100, 150, 200 AU. So without doing anything, these objects are going to be discovered nightly, a combination of using information from the Minor Planet Center. So there'll be annual catalogs that will only use LSST only, but the idea is that not to be, basically not to redetect Ceres or redetect Pluto, right, and not know it on the daily products. And this will all be sent to the Minor Planet Center basically the next day, and the Minor Planet Center is actually going to be doing the orbit fitting. But if you want to do your statistics, you might want to do that in the annual data releases, or in the first year, there'll be one at the 6-month mark. So it will come out basically a year later because it takes 6 months to process 6 months of data. So the idea here is, right, is that for free, you're going to be getting these detections also of Oort cloud comet, and incoming Oort cloud comets will be detected. So not just the Oort cloud, but I was tasked to talk about that. And that, this pipeline is using sort of tracklets. So it's 2 observations on a night and a nightly pair. Unfortunately, that's the way we have to do it. And then a couple, right, it's asking for 3 tracklets over 14 days. So the folks at UW are commissioning this thing now. They are, I think, finding things, though we will maybe know about that on the 23rd. But the idea is that they've at least acknowledged that they've been able to associate known objects and find them in LSST images, so in ComCam images. So this thing is nearly ready to go, and we have an actual working solar system moving object pipeline, which I think is really exciting. So whether you want to detect these things or are interested in observing, this is just going to be at your doorstep ready for you to be able to compare to. What I want to highlight is that the pipeline is only going to go out to about here. So the pairs are taking about 33 minutes apart. So we're going a little past 150 AU in terms of distance, which means bespoke algorithms are going to have to get us further if we want things more in that inner Oort cloud region, further right, or even further. And so I'm sure everyone who's looking for Planet 9 has their pipeline ready to go to do this, but it is something pipeline finding these moving objects if we don't want to wait for siloed groups to announce this stuff. But the data is there, right? And that's, I think, an opportunity for people to, when this data starts coming in, that the moving object pipeline for now has a requirement to only look for things that have moved between the 2 images. But again, Sedna is sitting out at 80 AU, so it would have been found. So there will be, there's a multitude of data, right, available, right, where I think there's things that the community themselves can do. Both the data and the detections are already going to be found by Ruben, but also doing more beyond that. And so one thing I just want to highlight that is also maybe observationally now maybe confusing, and I don't know if this would count as the inner Oort cloud, is that the New Horizons folks are claiming with their Subaru search is for a 3rd flyby target, is that there's an uptick in objects around 80 AU after the Kuiper Cliff that they didn't expect. Now, this is with stack and shift. These are with basically 27th magnitude detections. Some of those may or may not be real because it's stack and shift. So in the paper, it's not clear to me that all of these are real. They talk about how they do some assessment on this. But if we take it at face value, they're arguing that for where they looked, right, this is a sufficient enough increase that they're proposing there may be a belt like the co-classical belt sitting out at 80 AU that we just haven't seen because it's about 27th magnitude. So to highlight using a survey simulator, my graduate student Ryan Little, really early results. If you just take what Ruben's going to do face value and you take what Fraser's predicting, even with the pipeline that's not so great at finding things out to, only going out to about 120, 200 AU, it finds 10 objects. So if it's real, we might start seeing them in the LSST, but stack and shift is going to be really important, or shift and stack rather. It's going to be really important to be able to probe deeper. And again, there's tools to do this. But again, it's something to highlight as an opportunity, right, of things that we can probe and how that then ties into, right, the inner Oort cloud and Oort cloud together, I think is interesting and I don't have a handle for. So again, just want to highlight this as an example. So mainly my goal here is to be the cheerleader for LSST because one, the data's coming. This has been things we've been promising and talking about and thinking about. But really, right, as the joke was last year, Wajer said, take your vacation now because there's no sleeping when this thing turns on. And so these detections will hopefully be coming in, right, as the survey is discovering. We're actually observing. We're very much trying to push as a community, or the Solar System Science Collaboration is pushing to make sure that there's incremental template generation so we don't just get these at data release, we get them as they're coming. Both because we can do the interesting science if we do find these, in another Sedna-like object, or an Oort cloud object, or anything else that's weird. But also just to highlight, we're going to get colors as well, right? With all these filters, we're going to get rough surface colors. We're going to get some light curve variability. And so then again, how does this influence what we see? So I'd love to know that now that if we take all of our models for these different things, what should these things look like, right? So how can I help differentiate between these? If we do start seeing a bunch of Sedna-like objects, great, what color should they be? And if they're not what you expected, what does that tell us? And so I think we're now going into, as I joke, Technicolor from black and white TV. And just to give you the full scale, if I haven't sold LSST and told you the future is now bright, I think, for this field, and that also for Oort cloud comets, because again, we're going to see a lot of the long period comets coming in for a good portion of their orbit, and also very far away for distance activity. Just think about, this thing observing just over one night. So just to give you a scale of how much covered it does in a single pointing of 45, basically 45 times the size of the full moon, right, fits in a single pointing. And it's real and it's actually starting. So me, the pessimist, is optimistic now. Like, this thing is going to happen. And how, my question to all of you is, what is it that observers, right, need to do to get ready? And what is it that we can start doing to just entangle between these? Just like Morby talked about, right? Again, if there's a planet 9 and not, that's now a prediction we can test whether we see those objects there. Because this thing's going to find it one way or not. This is our, really going to be the thing that finds solar system objects. It's going to be the discovery machine, the follow-up machine for more than the next decade. So that's my cheerleading role for the LSST. A little bit about Oort cloud, inner Oort cloud, but really to say, how do we connect these together?
Okay, we have time for questions. We've been asked to give our names and affiliation if you want to ask a question. So I'll start off. I'm Hal Levison from Southwest Research Institute in Boulder, Colorado, and we can take questions. Sławomir.
Yeah, so I'm Morbidelli from France in Paris, and so you said you are optimistic that Vera Rubin can find a planet if it's there. But you also showed that the cadence of frames is such that you can discover objects up to 150 AU from the sun.
You can do more. You can do better. It's just that this is what the pipeline is. This is what you get for free.
Okay.
So, Mary Urich gets paid and has to deliver this. Like, this is part of operations readiness.
So I just wanted to highlight that there is a constraint that is often overlooked, that Planet 9 cannot be closer than 600 AU today.
Yes.
Otherwise, we would see perturbations in the motion of Saturn that Cassini did not detect.
But the brightness, right, is,
is
21, 22.
I wanted to ask you if you can detect an object that is basically not moving much. So
I can do it, right? Any of us can do it with our own pipeline. But Rubin requires, and again, this is partly because we have to play nice with the people that do NEOs. Part of the problem of trying to do the whole solar system is that they need that too. So the requirement in the pipeline in terms of, Rubin runs by everything is requirements and data management documents that have to be approved, is that you has to search for motion between the two observations. If you search for motion over 2 nights, then you can be stationary.
Okay.
Right? But guess what? We have to write that pipeline. And I'm sure there's people that already have one. I mean, it's not hard, right? But someone has to do the data processing. So this is the thing of Rubin's giving us a lot of data, and it's giving the baseline, right? But it can't do everything. And so I'm sure people have a pipeline. The question is, will people share those results, or will we see paper come out 2 years from now, right, saying here's all the detections versus putting in the Minor Planet Center, where everything that's basically found from 150 or 200 AU lasts. And again, this is assuming every observation's at 33 minutes. So there's 10% of observations that are taken in triples. So they go back again to a field, so that'll get us further out. So there's some of these fields will go, further out just because they've got an extra pointings, because people that do fast transients care about seeing if things change color. So we benefit from that. But I think somebody's got to put in a funding proposal or be running this nightly, right? If you want to be looking if you want to directly find Planet 9, it'll be in the data, but Rubin's not going to put a press release out saying their pipeline found it. And just to highlight that, because sometimes people think that the moving object pipeline is just going to go out to 2000 AU, and it's not.
Go ahead, Julio.
Just for curiosity, and I am amazed by the number of comets that can be discovered with the LSST. will it be possible to notice, to detect activity, because many of these comets will be very far away from the sun? And then what is the resolution? What level of activity the comet should have in order to be detected as a comet?
Yeah, so I probably should let Colin Snodgrass answer that. So I'll say something and then he will correct me if I'm wrong. I mean, basically they're so far away, you're not going to like get any resolution on them unless they're maybe really so massively active that you know, it's highly unlikely that they'll be that active that you'll see something out that far away. But I think the other argument is that probably if you're detecting them, it's because they are active. So I think spectroscopy and the follow-up observations are going to help tell you that. The reality is I think that's where you can start comparing models of what we'd expect if they were more Manx-like, right, and not active to ones that are we getting the right detection rates? And some of those things I think we can do with survey simulators. Or also by monitoring, right, if these things had an outburst, then we would see change in brightness that would maybe be more reflective of that. But I should let the LSST comment expert that I usually refer to see if has any other comments on that.
Yeah, no, that's basically all right. I'd note that this thing's an 8-meter telescope, so that, you know, in good seeing, the resolution's also pretty good, even at quite large distances. So we will get some morphology even quite far away if these things are active at large distances.
Okay.
Bryce, introduce yourself.
Hello, I'm Bryce Bolin from Eureka Scientific. Recently, there was an object discovered that has a semi-major axis of 800 and a perihelion distance of 45. Where does that fit into your phase-based diagram showing the delineation between inner Oort cloud objects and scattered disks?
So our argument was it's right on the edge. So we argued you needed to be at 45. So if you're right at 45 at 800, you're at an edge. And so I'd be worried about it. So again, I think it's, you know, we say greater than 45, then it's fine. So if you're right at 45, I mean, again, what's the right actual place to put that? Unclear. So I think that's where the dynamicists need to tell us better than, you know, me looking at a plot from Ramon Browser and talking about it. Right, using these simulations of actually, I think, looking at what's the criteria for that. And I think that includes doing the dynamical integration for it. So I haven't seen on that one what the integration for it is to see if it has no influence significant influence from Neptune. But yeah, I think that's edging in the place where those things are more, you know, interesting, more in that, you know, region. So I'd be more confident using that and say for statistics than using, you know, something more inward.
For reference, the object is 2017 OF201.
Yep. So I forget if that's far out or one of the ones. It's one of the other ones from Scott Shepard. So I think it's in the list, right? But I see a lot of people pulling things from perihelion 40AU, and it makes me sort of shiver and sort of twitch a bit of whether those objects are in there. And I don't have the right answer. This is, again, an observer sort of perspective looking at, asking a dynamicist to dump a whole bunch of particles in and see what happens. So I think that's a question I have is, what's the right thing we should be doing to tell people that are actually doing this Plan 9 statistics, what things are the right objects to be taking and including, as you brought up, Bryce?
Well, we should move on. Let's thanks Nate again. Our next speaker is Paweł Wajer. Did I pronounce your name right? And he's going to be speaking on the origin of Sednoids and Oort cloud populations by means of the sun's birth cluster.
Yes, my name is Paweł Wajer. I work with a group of Professor Hans Rickman in Space Research Center of Polish Academy of Science, and it's a great honor for me to be here. Here we can see a title of my presentation. I would like to say a few words about origin of Sednoids and Oort cloud objects. Here is an outline of my presentation. At the beginning, I would like to tell a few words about our model. Next, I would like to tell more about population of Sednoids and Oort cloud comet in our simulation. Next, about sizes of these objects. Next, about distribution of inclination of Sednoids and Oort cloud comets. And finally, I would like to tell a few words about three known now for such objects. Here we can see how planetesimal from inner part of our solar system can be extracted into Sednoid and Oort cloud objects. Sednoids are objects with semi-major axis between 100 to 1600 AU, and Oort cloud comet from 1600 to up to 1 million AU. Major planets mostly change semi-major axis energy of these objects, and its perihelion distance is constant, and external forces can change orbits, perihelion distance and angular momentum of this object, and this object could be extracted to Sednoids or Oort cloud comets. Next slide. Here is a description of our models. We generated 4 models. They differ in 2 key aspects: concentration of stars and time of gas removal. We generated 4 clusters with large Plummer radius and small Plummer radius. These clusters are less concentrated, and these clusters are more concentrated. In each clusters we generate, we choose 6 solar templates, and we generate finally we generate 17 solar templates, and we use 4,000 planetesimals scattered by planets Jupiter and Saturn. Time of simulation was 10 million years. And here we can see that some results of our simulations. We have at the end of simulation we counted number of Sednoids objects as defined are here, with perihelion distance larger than 16 AU, and Oort cloud comets for cluster A, B, C, and clusters D. As we can see, 0 counts of Sednoids are common in clusters A, as we can see here, in cluster B, and in clusters C, but not in clusters D. In clusters D, in fact, we got many Sednoids. And this slide shows a number of Sednoid, this slide shows statistics about sizes of sednoids and about sizes of sednoids. The sednoids are divided into two parts: kilometer-sized sednoids and larger sednoids with diameter larger than larger sednoids with diameter larger than 40 kilometers and kilometer-sized small sednoids. As we can, and here we have listed stars only with sednoids where we have more than 1 million sednoids. In case of clusters A, we have 4, and so on. As we can see, we got billion of small size kilometer sednoids in all cases. And our result shows that the predicted number of sednoids is too small in the case of clusters A, B, and C, and only D cluster can produce enough large sednoids to fit with the observations. Here are our results about Oort cloud comets, and we predict that Oort cloud population with about 10% of currently estimated Oort cloud objects. The results are for A clusters, B, C, and D clusters. In inner core population, outer core population, total population, and we have ratio between outer and inner ratio and inner populations. In this slide, I would like to show distribution of inclination of our objects from our simulation. Red circles are sednoids, red dots are sednoids, black dots are Oort cloud comets. We have two plots, A and B clusters, less concentrated clusters, and C and D cluster more concentration clusters. And this tighted line at inclination equals 25 degrees denotes the upper limit for the all now 4 observed sednoids. And as we can see, in case of clusters A and B, more sednoids have. I would like to say about axis. The radial distance of object from the origin is logarithm of its semi-major axis, and the angle between positive x-axis is its inclinations. And as we can see, in case of A and B clusters, more of objects have inclination smaller than about 30 degrees. In the more concentration clusters, more sednoids objects has inclination smaller than about 17 degrees. And in both cases we got large fraction of sednoids with retrograde inclinations, as we can see in case A and B clusters, and in case of clusters C and D. Okay, and in this slide I would like to show our result. Can we predict Sedna-like objects? From our simulation we got that estimated number of Sedna-like objects. Sedna-like object means the size of Sedna and its orbital elements is the maximum value of about 500. But we also calculated expected number of visible Sedna-like objects, and in this case the number is smaller than 1. So from our simulations, we can see that the Sedna could be detected, but this object and this object could be detected because it's visible. I would like to point out that our results rely on the assumption of very steep size distribution for large objects. This assumption might be, of course, unrealistically steep. Conclusions. From our object, we got that a large number of kilometer-sized sednoids is predicted to exist. The sednoid population has a very big and important retrograde fraction of objects. In case of clusters A, B, and C, the predicted number of sednoids is too small, and we predict that our cloud population is about 10% of currently estimated objects of currently estimate Oort cloud objects. Here are my summary of our main results, and thank you.
I'm Ben Gustafsson, Uppsala. I wonder about what constraints we do have concerning the size of the birth cluster. I mean, could it be, say, 4,000 or 5,000 stars instead of 1,000?
1,000 stars.
Yeah, could it be greater? And if it were greater, would that solve your certain missing objects?
It would be greater. I'm not sure, because the number of sednoids mostly depends on concentration of stars, not the number of stars. As we can sorry. As we can see in the cluster. In this cluster, the stars are very concentrated. The planar radius is small, and we got a larger number of sednoids.
Bryce? Oh, Bryce.
Thank you. Hello, I'm Bryce Bolin from Eureka Scientific. So I see here that you examine cases for early gas removal versus late gas removal, as well as small and large plummer radii. However, do you examine at all in your simulations differences in timing of the dispersal of the birth cluster and its effect on the results?
Timing of dispersal of what? Can you repeat?
The birth cluster. Does the birth cluster's lifetime affect the results if you have a early dispersal of the stars versus a longer timescale dispersal of stars?
The larger time of dispersal of stars will be shown in our next presentation.
Okay, sorry.
So in this simulation, the time of dispersal was small. The total time of simulation was 10 million years. In case of all.
So this is Hal Levison again. I'd like to understand exactly the physics that are in this model. Do you allow the birth cluster to disperse? What kind of dynamical integrator do you use? Do you take, I have several questions. Do you take the potential of the gas of the cluster into account? What's the calculation look like?
And gas drag.
And gas drag. Yeah, I wasn't going to ask about that gas drag, but this is a hard problem, starting out with things on circular orbit near Saturn and actually having the cluster dynamics in it. So I would like to try to understand exactly how you did the problem.
Yes, it was very difficult to simulate because in our cases I don't know how to say.
Well, we can say that we simulated stellar clusters, 1,000 stars to begin with, and a rapid removal of the gas. And this leads to clusters that just fly apart.
Yes.
And in 10 million years, the clusters have, in almost all cases, flown apart. So the clusters aren't there anymore.
Okay.
In the new work that Tomasz will describe, we're going to do it differently.
Well, I think that that's physically the right thing to do, right? Having the cluster fly apart. But I'd still like to understand what integrators did you use? What integrators did you use?
N-body 6 plus GPU. It's an ORSET code, the old one.
Yeah, the old ORSET.
Yeah.
Yeah, cool, okay.
And you have gas drag because you have gas. So do you have gas drag? You
No.
have a disk of gas or not?
In this work, we did not include gas in the dynamics.
Okay.
However, we looked at the Brasser et al. Paper, and we conclude that, yeah, for small size comets, the possibility to get extracted is heavily reduced. So the chances are small, but they are not zero.
Okay. But the numbers here were
That's why we could predict a reasonable number of small samples.
Any other questions? Yeah, Julio.
Well, I am Julio Fernandez from the University of the Republic in Montevideo, Uruguay. My question is about this number of 4,000 planetesimals that you simulate. That is because this is very tricky because the scattering of planetesimal, cometesimal could have been larger or smaller. That depends on the model that you use for the formation, evolution, and scattering of the population of planetesimals in the other planetary system. And then it seems to me in the model a bit arbitrary to take 4,000 planetesimals. If you take a larger number, you will get more Sednoids. You take a smaller number, you will take smaller Sednoids produced in the model. Then, what is the hypothesis behind this number?
Here, we simulated numerically 4,000 planetesimals in our numerical models. We use era 15, but here, when I showed the and here at this slide, excuse me, at this slide we have a number of extracted objects from these 4,000 populations. But But at this slide, we have expected number of sednoids when we use some model of distribution of objects, of sizes of objects. So in other words, here we have rescaled number of sednoids outcloud in comparison with this table. In other words, we assume some distribution of sizes and number, and of course, total number of objects.
Yes, these are tracers, but what is the total mass that they represent? These 4,000 planetesimals. Given your size distribution, what is the total mass that is represented by these 4,000?
I don't remember now.
I don't remember either. But we scaled the population of Jupiter-Saturn planetesimals to be the same number and the same mass as the trans-Neptunians.
Okay, okay. So 20 of mass is probably.
Yes. Mm-hmm.
Well, I'm afraid we have to move on to our coffee break. Thanks, speaker again.
Yes, the Polish names are always complicated. Instead of Tomasz, I prefer Tomek. So, Tomek. My name is Tomek Wiśniowski, and I am one of the members of Hans Rickman's group. And this presentation will be to some extent the continuation of the previous one. You can see that only the subtitle is changed. The main title is the same because we continue our work now. Let's start from the conclusion that our previous work, where we used a burst cluster and Jupiter-Saturn planetesimals, did not explain the observed flux of the long-period comets and the existence of sednoids. We need another source of planetesimals. On the other side, it is worth noting that the burst cluster, which typically lasts from a few to 10 million years, sometimes may survive much longer, even 100 million years or more, and transform into typical open cluster. And so we can use this in our simulations, and maybe the Sun was born in such a cluster. If so, we have new possibilities, namely that we can use the planetesimals which were scattered by migrating Neptune. We have much more time for this. And of course use the tidal forces which can extract the objects during this long times from the solar system. This idea is not new. We have old precursors. Fernandez and Bernini and Kaik and Queen obtained good results, but only for the innermost core of the Oort cloud. Also, many later papers have a problem with explaining the outer halo of the Oort cloud. Here we have to mention more realistic and more advanced modeling, where the Nice model were used, and they used the trans-Neptunian source of planetesimals, but without a burst cluster. So still the issue is open, and here we enter, trying to combine everything, namely the Neptune's Nice model migration, long-lived burst cluster, galactic tide, and trans-Neptunian source of planetesimals. When we would like to go this way, of course we need stellar clusters. And the first task for us was to create such clusters. We used software McCluster to create initial form of the clusters, and then N-body 6++ GPU to perform the simulations. And our task was to create 12 clusters which were able to survive 200 million years. It was not an easy task. Our initialization and initial conditions were mentioned to the left. All the clusters were initially 5,000 stars, and the Plummer density model we used for all the external tidal field represented by point mass galaxy. And of course, because we deal here with burst cluster, we also include gas, which was present during 1.5 mega year. And the important are the model parameters. What differ these clusters? The most important is tidal Plummer radius ratio, marked here as concentration factor, and we use different values of this parameter. Then different values of two different values of star to star plus gas ratio, that is marked as star formation efficiency. We also introduced the fractal geometry, so not all clusters were have 3D geometry. Binary fraction, that means that some stars are, of course, in binaries, and we use two values, 10% and 30%. And mass segregation, that means that in perfectly segregated cluster, the small mass stars are on high energy orbits and opposite. In such case, the mass segregation parameter equals 1. So as you see, we used either intermediate segregation or do not use segregation at all. And please don't think that this is easy to obtain such a cluster, that we performed 12 simulations and then have 12 clusters surviving 200 million years. And the number of extractions of simulations made here is about 100, I think. Sometimes we have to repeat with different random seeds many times the simulation with these parameters to obtain the cluster which survived 200 million years. What we mean by saying that the cluster is alive? This is an arbitrary condition that after 200 million years, the number of stars inside the tidal field, tidal radius in the sphere with tidal radius still must be greater than 500. And we have this cluster now ready with some time resolution. Because time step is as high as from 1,000 to 3,000 years. And so we can answer the question where each star of this cluster is in each moment by, in every moment by interpolation. Let's have a short look at cluster portraits, initial cluster portraits. Here we have two exemplary clusters. One of the left one is was constructed with 3D geometry and is spherical symmetric. And the second one is uses a fractal geometry, which is preferred by a hierarchical stellar formation model. You can see here 3 circles. The red one means the core radius of the cluster. The thick black is the tidal radius. And the thin black is the tidal radius, but including gas. So it is during the first 1.5 million years. And now the glimpse on these clusters after 100 million years. Here the circle means the tidal radius. You can see the stars which are escaping from the cluster and forming tidal tails, which extend into a spiral shape due to galactic differential rotation. Note that after such a long time, we have no sign of the fractal geometry at the beginning. It is removed from the cluster quite early. Having the cluster, we can plan our work for future. Now we are going to use high resolution simulations lasting 200 million years with use of solar system, cluster, and galaxy. What does it mean, high resolution? In case planetary simulations, we must use, of course, much higher resolution, namely days. Of course, this is dynamic and depends on this software, but we need much higher resolution. As a solar system, we use the Sun plus Neptune plus 4,000 trans-Neptunian massless objects. Of course, we use the NICE model migration scheme. And in this model, the instability starts at about 30 million years when the Neptune starts to intense scatter the planetesimals. Cluster, of course, acts through its tidal field and close encounters, which we also handle, and the galaxy through galactic tide and field style encounters. Of course, it is not everything is clear. There is a risk that the Oort cloud is purged by the cluster. Nordlander and at all obtained the cluster ready at very early times. So when the cluster is ready, very early, the star cluster, when the Oort cloud is ready quite early, the star cluster can only erode this Oort cloud. But we have on the other side the more long-lived source of planetesimals. So maybe purgings and extractions work in parallel. Who knows? There is also the risk that outer halo is depleted by the tidal purging. This means that the tidal forces may start oscillations in the outer halo, and this may lead to escaping of the planetesimals from the outer halo. But there is also a chance that the Oort cloud halo will be repopulated, because we have all our system immersed in galaxy for giga-years. So we may have a strong exterior perturbation by GMCs, clusters, or massive stars. This can lead to repopulate the Oort cloud halo. This is my last slide about Planet 9. I think everybody in this room has the last slide about Planet 9, something like this. Morbidelli said practically everything, and So I have only one remark that the planet 9 may be among this as a planet-sized object among this planetesimals extracted by ejected by Neptune and scattered by Neptune and then extracted by long-lived burst cluster. So we need long-lived burst cluster to explain the existence of planet 9. Thank you very much. Your question, I will try to answer.
Questions?
Oh. Hi, Tom Kooten, University of Washington. Could you explain the motivation for using a point source for the galactic tidal field rather than, in my mind, I might be wrong, I feel that, the disk part of the galaxy, in my mind, dominates the tide rather than sort of the, overall mass of the galaxy. Yes?
I think I can answer that. We actually, in our simulations, we will use the disk tide, although we use the point mass galaxy just for the effects on the cluster. For the planetesimals,
yes.
we will use
Okay,
the disk
okay.
tide.
Oh, very good. Okay.
So only the cluster will make this galactic tide. And now the work will be different.
Thank you.
Yeah.
This is Bryce Bullen from Eureka Scientific. So the question I have is so you showed very nicely this fractal dimension 1.6 arrangement of the different stars and the clusters and so on. And you show very nicely how it is dispersed rather quickly. However, does the dispersion timescale at all depend on the migration history of the sun's birth cluster?
To say the truth, this is not our point. We only introduce the fractal dimension into our initial clusters and only look at the final effect. And we did not analyze what is the time when the fractal dimensions move and what are the parameters of such a moving. So I can't answer for this.
You may see something on the poster by Kowalski.
Thank you.
I'll take the next question if it's okay.
Okay.
Okay. I always thought the argument was that the sun did not form in an open cluster or spend time in an open cluster because the probability of having a really close encounter would actually, the encounter would be close enough to actually destroy Neptune's orbit or perturb Neptune's orbit, right? And that's an argument going back to Fred Adams a decade or a half ago. So I was wondering, I know you haven't put your cover belt in or your planets in yet in these calculations, but you should have statistics for close encounters between your stars, right? And I'm wondering whether you've looked at those statistics and can argue that our solar system could survive in such a cluster before you move on to actually putting the solar system in.
Yes, but this is something that we need. We have a full control about close encounters between stars of the cluster.
Well, have you looked at the statistics yet to convince yourself that the solar system would survive?
I don't know. I don't understand your point.
Well, we can talk about it on one of the breaks. Go ahead. We have time.
Okay. If I understood you right, you claim that the existence of planet 9 requires a long-lived solar cluster.
Okay, maybe this too strong word.
Yeah.
This is accepted scenario, let's say.
Any other questions?
Colin Snodgrass, University of Edinburgh. A naive observer's question for dynamicists. You say you've used point mass for the galaxy, and do we not have an influence of spiral arms? Or if we start with the cluster in the spiral arm?
Influence of
The spiral arms in a galaxy, or does this not make a real difference for the dynamics?
Yes, this will be taken into account in planetary simulation. When we build stellar clusters, we use galaxy only as a point mass.
But the disk is the second order perturbation, and then GMCs and the tides due to that are important. The arms are just higher densities of GMCs.
Okay, doesn't make a big difference. Okay.
Yeah, the mass density in spiral arms is only like 10%.
Yeah.
Okay.
Yeah, so
And here
GMCs are probably the third order.
Yeah.
Okay.
Well, let's thank our speaker again. Next is Melania Saillenfest. Did I pronounce it?
Okay, so good morning. It's a real honor for me to be here today and give a talk to such a distinguished audience. So as we saw already this morning, the inner limit of the Oort cloud is still a debated topic, mainly due to the lack of observational constraints. So in this talk, I will try to review the different dynamical mechanisms at play in this region of the solar system, just in order to locate this inner limit of the Oort cloud, or at least see whether we can find a definition of where it could be in a dynamical point of view. So I will first step back to the foundational works about this transition between what we could call the scattering disk, the Kuiper belt, and the Oort cloud. And in particular, I will mention the famous paper by Jack Hills about what we sometimes call the Hills cloud. So this is a general picture of the solar system as it is today, okay? And we can see the location of the Oort cloud, which is perturbed by the galactic tides and passing stars. And because of the effect of galactic tides and passing stars, some of the comets can be injected toward the observable region, and so we observe a long-period comet. And this is this way that we can know that there is an Oort cloud out there, okay? And what Hills noted is that the fact that we observe some kind of inner edge of the Oort cloud in terms of the semi-major axis does not mean that comets cannot exist. Comets do not exist with semi-major axis smaller than this value, 20,000 astronomical units. It is just that these comets are not perturbed enough so that they can reach the observable region. And Hills said that it should exist also an inner Oort cloud that would be inert most of the time, so the orbits would remain rather fixed during billions of years, and be only perturbed when there is a very close stellar passage. And actually, at the time Hills published this article, only the passing stars were considered. The galactic tides were not introduced yet in the dynamical models, but this idea of Jack Hills remained the same, even if we introduce the galactic tides. So let's see how we can find this kind of inert region in the solar system in a dynamical point of view. Does it exist? We will see. So in this perspective, I really like this picture by Tabaré Gallardo. We just integrated a lot of planetesimals, fictitious planetesimals, massless particles, under the effect of the giant planets on their current orbits. And we can see here their tracks in the plane of the perihelion distance on the vertical axis and semi-major axis on the horizontal axis. And we can clearly see two different kinds of dynamics. Okay, the particles going vertically under the effect of mean-motion resonances with Neptune, and the particles going horizontally due to planetary scattering, which is actually due to the overlap of these mean-motion resonances. And on this graph, we can also see a white square here, where no small body can enter during this simulation, which I think it lasted 1 gigayear or something like this. Okay, and in this region, both the resonances and the planetary scattering are inefficient. Okay, so if we put a small body here, it remains here for the duration of the integration. It does not move out of this region. So this is an inert region that resembles what Hirsch had in mind. And actually, as we will see, what we could call the Hills cloud, or the inner limit of the Oort cloud, lies at a transition between many different kinds of dynamical mechanisms. So we have mean-motion resonances and planetary scattering, but also the secular precession driven by the giant planets, and of course, the action of external effects as the galactic tides. So in this talk, I will review these different dynamical mechanisms and see what are their effects and their limits. So we start with mean-motion resonances and the scattering dynamics. So in order to understand what can be the effect of mean-motion resonances, we just need to average the dynamics over the fast angles in order to obtain a tractable model. So by doing this, we obtain one constant of motion, which is the third component of the angular momentum of the small bodies, because of the symmetry of rotation due to the quite coplanar and circular orbits of the planets, and two dynamical variables, okay, with two angles. Sigma, which is the resonance angle, and omega, which is the argument of pericenter of the small body. So we have 2 degrees of freedom here, but actually we can do even better if we notice that the evolution of the resonance angle sigma is much faster than the evolution of small omega, the argument of pericenter. And this is because of this classic hierarchy of time scale. So if epsilon is the perturbation, we see that indeed the variation of sigma scales at the square root of epsilon, which is much faster than epsilon itself. Okay. This is what we call the adiabatic approximation. And just a bit more into detail. So here we have a picture of how it works, okay, this adiabatic approximation. So this approximation says that the variations of small omega are so slow that for a short amount of time we can consider that it is fixed, okay? And this way we recover the classic pendulum-like dynamics for the resonance angle on the horizontal axis here, okay? And actually, we can even draw a parallel between the motion of a simple pendulum, like this, and the motion of a small body beyond Neptune. Okay. We have the trajectory of the small body here in red. Okay. So now, if small omega varies very slowly, this picture is distorted like this. It is just like if the intensity and direction of gravity changes very slowly over time. So this distorts the resonance island. It becomes here distorted and shifted toward the left. Okay, but the adiabatic approximation says that something is conserved during this motion, and this is the area inside the trajectory. And if we have this new conserved quantity, it means that we can remove again 1 degree of freedom from the system, and we obtain an integrable model for the long-term dynamics inside the resonance. And this way we can plot level curves like this of the phase portrait, with the black lines here being the level curves of the Hamiltonian function. So each line here can be a trajectory of a small body inside a resonance. And this way we can explore all the kinds of trajectory that can be produced by the mean motion resonances. So on the left here we have a full numerical integrations showing the evolution of a fictitious particle in the scattering region. So at first we see that the semi-major axis jumps in a chaotic way, but then the small body is captured in a mean motion resonance. And here it is a 237 mean motion resonance, a very high order mean motion resonance. So as soon as the small body is captured, we see that its pericenter distance oscillates with a very large amplitude here, almost up to 70 astronomical units, okay? And we see that the red point here follows very nicely the level curves given by the analytical model. But actually it is not so simple, because some kinds of resonances, the resonances of types 1, 2, something, are a bit more complicated, because for some values of the parameters, there are two sub-islands inside the main island, as we can see here, okay? So there are three different kinds of possible oscillations inside the resonance. So on the right island, on the left one, or around both of them, okay? This is a generalization of the Lagrangian points. And it can happen during the variation of the slow variables that one of the two inner islands here shrinks and even disappears, okay? So in that case, the red area here cannot stay constant because the small body is forced to cross a separatrix and to jump to another kind of motion. And in that case, we will see that this kind of transition can have very interesting dynamical effects. So again, this is on the left full numerical integration showing the evolution of a fictitious small body. At the beginning, it is in the scattering zone. Then it is captured inside a 1 to 13 resonance here. At that time, the pericenter grows again to very large values. But this time, we see that when the trajectory crosses the gray region here, that is, when there is a separatrix crossing, then the pericenter distance starts to oscillate with a very small amplitude, and it stays almost constant at very large values for billions of years. And we can understand this kind of dynamical evolution by looking at the phase portrait and where is the separatrix of the resonance. So at the beginning, when the object is captured inside the resonance, we see that the red area here fits quite well inside the big resonance island. But then, as the dynamics inside the mean motion resonance increases the pericenter distance, the resonance island shrinks, okay, up to the point that the object is forced to cross the separatrix and suddenly adopt a new kind of motion. And in that case, you see that the conserved area, which was the small red one, becomes the big blue one on the left. And by chance, the new trajectory adopted by the particle is such that if the small island, inner island, reappears then inside the resonance like this, the separatrix is either completely outside of the area, or it disappears again, or it is completely inside like this. So here, the object has made a complete cycle. It is returned back to the original location where it left the small resonance island, but it has a very small probability of being recaptured by the resonance. So it stays there with a very small variation of the pericenter distance for billions of years. This is some kind of trapping mechanism that can freeze objects with very large perihelion distance, even if the orbits of the planets remain the same, with no migration, just today's solar system. And this mechanism of extraction can be represented here on this schematic picture. So in gray, we have the scattering region, and the horizontal axis is the semi-major axis. And the vertical axis is the perihelion distance and inclination. Okay. So when we go up, the pericenter distance increases, but also the inclination. And in white, we can see isolated mean-motion resonances, so the portion of mean-motion resonances that do not overlap with other resonances. So we have a small body in red. Okay, so at the beginning, it is in the scattering zone. It can be temporarily captured inside a mean-motion resonance, and this resonance can either deliver it back to the scattering zone or extract it from the scattering zone by increasing its pericenter distance. And then we have this kind of trapping mechanism that can just freeze its pericenter distance to very large distance. And there is a recent paper by Konstantin Batygin that shows a way to compute an analytical expression for this limit between the scattering zone and the region where only isolated mean-motion resonance exists. And so the fact that we have a mechanism that extract objects and freeze them to high pericenter distance should create gradually a reservoir of distant small bodies. And indeed, this is what we obtain here. So we have integrated a lot of fictitious small bodies in the scattering region. And after, I don't remember, maybe 2 or 3 billions of years, we just noted with a blue point those that had triggered this mechanism and which have now frozen pericenter distances and inclinations. So indeed, we see that we create a few objects in this regime, okay, which have very large pericenter distance and almost fixed orbits. So these objects seem to be inert, indeed. So they resemble what Jack Hill says about a very inert region at the inner limit of the Oort cloud. But actually, they are still coupled with the planets because they are still close to a mean-motion resonance. And even if the probability for them to go back to small perihelion distances is small, it is not zero. Okay, so these objects are not part of the decoupled regime. They are not sednoids. Okay, and this is an example for this. This is a real small body. So the observed location of this small body is here. This is the blue cross. So the pericenter distance is quite large, okay? 50 or so astronomical units. But actually, if we take a closer look at this object, we see that it is very close or maybe inside the 1 to 3 mean-motion resonance with Neptune. And indeed, with this kind of separatrix crossings, we can explain its objects by a capture inside mid-motion resonance here. The pericenter increases, we have one separatrix crossing here, another one here, and we can reproduce the observed object. So this object is not detached from the effect of the giant planets. So one thing that we need to find a really inert orbit decoupled from the planets is that it should be outside of the reach of mean-motion resonances, or at least in the parameter space that does not allow resonances to have a strong effect like this. And this, with this, I arrive to the secular dynamics driven by the giant planets, that is, the dynamics driven by the giant planets, but outside of mean-motion resonances and outside of the scattering zone. So in that case, it is much easier to define a simple analytical model of the long-term dynamics because we can simply average the dynamics over all the fast angles, which are the mean longitude of the planets and of the small body. And in that case, again, due to the symmetry, we obtained a constant of motion, which is the von Seipel Lidov-Kozai constant, and the other constant, which is the semi-major axis, and we directly get a one degree of freedom system with two dynamical variables, again, the argument of pericenter and the pericenter distance. And if we look at what is the dynamics produced by this kind of model, we see that this is a very, very peaceful dynamics, okay, with very small variations of the orbital elements. Actually, we can explore all the parameter space and see that the largest variations in the pericenter distance are obtained near very, very specific values of the inclination of the small body, which are quite large, okay, 63 and 117 degrees. And even near these values of inclinations, the excursions of the pericenter distance are very small, or let's say rather small, okay, of the order of 16 astronomical units, okay. So indeed, this kind of secular dynamics driven by the giant planets, when we are outside of mean-motion resonances, is very quiet, very peaceful, almost inert, okay. But now we need to take into account also external forces that exert an attraction on these very distant bodies. So I will not enter into details here because there are talks dedicated to this later today. But just in short, the small bodies feel the effect of galactic tides and passing stars. And galactic tides, if we reduce it to its dominant component, we can see that we can obtain an integrable model of the dynamics. And the typical effect of galactic tides is to produce very large cycles of the eccentricity of the small bodies, like this. And this is typical of long-period comets in the Oort cloud. And the effect of passing stars is to sporadically randomize the orbital elements of small bodies. Okay. Like this, passing from a very flat distribution to a more spread distribution. So now we can take everything into account and try to find a way to include both the internal perturbations from the planet and the external perturbation from the galactic tides. This is what we obtain here. So we saw that in order to obtain something that is truly inert, we need to be outside of the reach of mean-motion resonances. So we just consider a secular model here. Everything is averaged. And we obtain a simple Hamiltonian with only two parts, the effect of the planets here and the effect of the galactic tides here. And we can just compare what is the size of these two terms of the Hamiltonian as a function of the semi-major axis. And this is what is represented here. So we see that for small semi-major axes, we are in the planetary regime. The planets perturb the most the small bodies. And for large semi-major axes, this is the contrary. This is the galactic regime. The particles are perturbed mostly by the galactic tides. So there is a transition between the two effects in this region at about 1,000 astronomical units. And we can also compute what is the orbital pole about which the orbits precess due to this combined effect of the planets and the galactic tides. And this is what is represented here. So we see clearly that there is a transition, as Morbi said this morning, between particles that precess about the galactic, the ecliptic pole here, the inclination is small, and those that precess about the galactic pole here with an inclination of about 60 degrees. So here in this region, we see that the two perturbations are almost equal, and they are both small. But does it mean that this region is inert? We will see that this is questionable. So here, if we take only the dominant component of this Hamiltonian with two terms, we have 2 degrees of freedom, and we can explore the dynamics by plotting Poincaré sections. This is what is done here. So for small values of the semi-major axis, we see that we recover the planetary regime with very small variation of the pericenter distance, or here the eccentricity on the vertical axis. For very large semi-major axes, we retrieve the galactic regime with these very large cycles in eccentricity. And in between, what we obtain is a very wide chaotic zone. So this is slow chaos. This is secular, and we can have an idea of the rate of this diffusion by the color scale here. So it needs we need giga-year to see an effect of this chaos. But over the age of the solar system, this is not completely negligible. Okay, this is chaotic, and we can see its effects, as we can see here. So here, this is a numerical integration showing the effect of this chaos, okay, for fictitious small bodies that are initialized in a very flat band in inclination or pericenter distance here. And we see, indeed, that over the age of the solar system, 4.5 giga-years, we have an effect. We can see an effect of this chaos. So the inclination spread, and it spreads much more faster for the particles with a larger semi-major axis, of course, because of the effect of galactic tides. We can also extract pericenter distances from the planetary region. And here we can see that we can obtain quite large extraction distances for the pericenter distance, even for quite small values of the semi-major axis, about 1,000 or 2,000 astronomical units. And because this is a very slow precession, we also obtain some kind of clustering of the orbital angles of these fictitious particles here. So we see that starting from an homogeneous distribution of the longitude of pericenter after 4.5 giga-years, so the vertical black line, according to the orbital elements of the initial orbital elements of the small bodies, we can see preferential locations for these angles. And this creates some kind of spiral structure in the inner region of the Oort cloud. And there is a talk dedicated to this just after mine. And by using these results, we can now map what is the region that we can really consider as inert in the solar system. And this is what is represented here. So the color scale here shows the variation in the inclination on the top row and in the pericenter distance on the bottom row over the age of the solar system due to this combined planetary and galactic tides perturbation. And we put an arbitrary limit, which is the black curve, just to say that we can consider that on the left of the black curve, this is inert. The variations are so small that we can neglect them. And on the right of the black curve, this is substantial over the age of the solar system. And we can see that by using this arbitrary limit, for instance, here for the pericenter distance, I put 10 astronomical units. Okay, we see that actually the inert, really inert zone is quite small. And it is located quite close to the planet, here at about, we can put it at about 500 astronomical units. Okay, and we also see that this limit is not smooth. It has many spikes like this, and we can explain very well these spikes. They are due to, well, this is a bit technical, but they are due to secular resonances produced by the galactic tides, which act at very specific values of the inclination. And we can locate the terms responsible for these secular resonances and compute the width of these resonances. And indeed, we recover the spikes that we can see in this graph. So to conclude, this is a picture showing the effect, where are the most efficient locations for all of these effects, okay, in the plane of the semi-major axis and the pericenter distance. So we saw that the mean-motion resonances with the planet can extract the pericenter distance from the planetary scattering influence, but the objects that remain trapped there are not totally detached from the mean-motion resonances. We have, for large semi-major axes, we have the galactic tides that can also extract the pericenter distance from the planetary scattering influence. And in between, we have this kind of secular chaos, which acts over a very long time scale, but which is not completely negligible over the age of the solar system. So in this picture, the truly inert zone, which resembles the most what Jack Hills had in mind, is the white zone. And we see that it is quite small, actually. And I plotted on this graph the four red points here as the known sednoids. And we see that indeed these bodies are detached from all of the kinds of perturbation. They are very frozen orbits. And for me, this is the four known bodies that resemble the most what Jack Hills had in mind back in 1981. And that's all. Thank you.
Question.
Yeah, so at the beginning
Introduce yourself.
Oh, okay, again. Morbidelli from Collège de France in Paris. So at the beginning you showed this plot from Gallardo that you said you liked a lot. It's a bit weird, very different from the one that Meg showed from Brasser and even your own in page 13.
Oh.
Because it gets a lot of decoupling up to 500 AU. Yeah, this one. Up to 70 AU in perihelion distance, and the plot that Meg showed from Brasser was the same, but the decoupling was limited to 200, and your own plot at page 13 also shows that decoupling due to resonances is effective only up to 200. So do you know how it got that?
Yes, it's because of the inclination of the small bodies. Here the inclination is not shown, but Gallardo, to plot this, used different ranges of inclinations, and I shows that very high inclination, yes. And actually, the effect of mid-motion resonance is very well defined in terms of inclinations and pericentral distance.
Me?
Meg Schwamb, Queen's University, Belfast. So on that, it sounds like one of the differentiators here observationally is going to be how much really super high inclination and retrograde stuff we find, both in the Kuiper belt and sort of in this region. Is that a good assumption, or what else do you think observationally is going to be useful? But it sounds like that's one key component is how much stuff do we even have out there that are on these high inclination or retrograde orbits?
You mean to distinguish what? Sorry?
I think in terms of understanding more about the inner Oort cloud informations and basically what the structure is even looking like, as you said here, with the distinction between, what Brasser showed and what your sort of plot showed compared to this.
Yeah, that's for sure. Finding much more retrograde orbits will allow us to sample all these dynamical regimes and see exactly where their limits are and so on. But in that case, I focused really on the dynamical part. So maybe we have very interesting dynamical regions, but which are not populated at all. This is also possible, okay? So we need to find many, many small bodies to sample everywhere we can find small bodies, but we will always have this problem, okay? There are not small bodies everywhere in the phase space.
I'm Daniel Eschhofer, Paris Observatory, same lab as Melaine, and you were mentioning the evolution along the Laplace plane for the precession and the spreading in inclination and perihelion, but I was saying also that stellar passages was also responsible for these spreading, so you haven't included them yet?
No.
So,
no, the effect of passing...
yeah.
Or maybe I can show that one. The effect of passing star is to sporadically randomize the orbital elements of small bodies. So maybe we can have a small body in the scattering zone that is suddenly transferred to the inert zone, or from the secular chaos to be transferred to the scattering zone. This is the effect of these sporadic stellar impulses.
I have a question. Can you go, and it's going to be a stupid question, can you go back a couple slides showing the delta? That's the plot. So I was struck by the idea that Planet 9 is actually in the region that you are talking about, if I understand correctly.
Yeah.
And the evidence people use are alignments in the angles for Planet 9, right, of objects that we observe. But that's not the plot. You showed one where converging angles. That one, right?
Yeah.
So my question to you is, can you explain the alignments people are seeing and attributing the Planet 9 by this chaotic diffusion?
Yeah, I did not look into details into this, but we hinted about this in our paper. We would need more efficient galactic tides to produce the clustering that we observe, because the objects are quite closing the Sednoids. But maybe if we find a way to increase the strength of galactic tides, this could reproduce some kind of alignment. But here also we see that we have two different values of clustering, okay, for the longitude of the pericenter. And I think that the alignment that is used to define the location of Planet 9 is based on only one specific values.
Depends on who you talk to.
Sorry?
Depends on who you talk to.
Okay.
There's at least 3 different definitions.
Yes.
So maybe there is a way. And I was also puzzled by the fact that the proposed orbit for Planet 9 intersects the plane of the ecliptic exactly where the galactic plane intersects the ecliptic. And why is that so?
Otherwise we would have found it.
Luck.
So maybe
the only way you get the effect.
Pedro Lacerda from University of Coimbra. And the location of this clustering shifts with the perihelion of the test particle, right?
Yes.
So that would mean that these Sednoids that are being discovered, depending on the perihelion of each one of these, the clustering moves a little bit. So maybe this is a way to test if depending on the perihelion of the object, if the clustering is moving around.
Yeah.
Because if it's Planet 9, it won't move. It will always be in the same place.
So maybe, if we find a lot of objects.
This is for 1,800 EU, and as Melaine said, none of the objects that are used for this analysis is so far out.
Yeah,
they are all, you said that, so that we should not fix
we need to make
our eyes on the right plot, I think.
We need to find a way to get a stronger galactic.
Very strong galactic.
We gave the correct answer.
Yeah.
Any other questions? Let's thank our speaker again. And our final speaker before lunch, so hurry up, is Luke Jones.
The galactic light theory or the migration history of the stellar plasma.
No, because the mass,
Okay. All right. So let's see, what do I do here? Is it? All right, which one's the? Okay. Okay, sorry. Okay, let's go back. Okay, so you may, I'm sure you recognize the names on the first line of this, and Christian Boget is a dynamicist in Argentina. You may not recognize the last 3 names, and they actually deserve the credit because they're the ones who actually found the phenomenon I'm going to talk about. They're at the American Museum of Natural History in New York. Okay, so this is a diagram just to emphasize that I'm going to be talking about what I call the traditional inner Oort cloud or Hills cloud. So this talk will be about things at thousands of AU, not hundreds of AU. Okay, so Morby already showed this, but this is just the some test particles at 6 time steps from our simulations back in ancient history, and just to show that the initially the orbits get scattered to large semi-major axes at low inclinations, and then eventually galactic tides and passing stars raise the inclinations. Okay, and this, again, Morby showed, this is just to remind you that the galactic plane and the ecliptic are inclined by about 60 degrees. Okay, so this is from a paper led by David Volkrolitsky, and the results I'll be showing you are based on a very similar simulation that David Nizvorny did in a more recent paper, where he examined various scenarios, including a cluster origin, but everything I'm going to show you is assuming the sun, that the Oort cloud formed in its current galactic environment. So the simulations included planetary migration, planetesimal disk beyond Neptune, and included the effects of passing stars. And we found that about 5% of the particles that we started out with survived to the present in the Oort cloud. And in retrospect, we should have paid more attention to that little clump with the arrow in the bottom panel, because the middle panel shows inclination in ecliptic coordinates. The bottom shows in galactic coordinates. And there's this little clump at inclinations near 90 degrees that we just didn't really think about much. Okay, so let's see, how do I play this? Okay, so this is the animation that they made at the Hayden Planetarium. So let's see, how do I play this? Okay, so this is supposed to be a simulation that they made for a planetarium show, flying into the solar system from well beyond. So you briefly saw this spiral, and then it's zooming in on the Kuiper belt. So now you can see the Kuiper belt and the orbits of the planets, and then it goes back out. So I'll just skip on from there. Okay, so this is basically a frame from that simulation, which only shows bodies with semi-major axes less than 5,000 AU. So it doesn't show the outer Oort cloud, and it doesn't show the Kuiper belt. So it just shows that you have this sort of spiral structure. So so you have a lot of things on nearly polar orbits, and then you get these sort of two spiral arms when you go a little bit further out. So what's going on here? So as we heard in the previous talk, you're in this sort of funny regime where everything is kind of slow. So for this talk, I'm going to take canonical semi-major axis of 3,000 AU and perihelion distance of 30 AU. Well, you can take the precession due to the planets as sort of an effective J2, and you get that the typical time scale is billions of years. And I'm going to ignore planetary precession for the rest of this talk. Okay, so for the rest of this talk, I'm going to take this very simple model where the galaxy is just represented as a slab of constant density, and Z is just the distance of a comet from the sun perpendicular to the galactic plane. So you have these two constants of motion, and you have this characteristic frequency. Let's see. Oh, there we go. You get this characteristic frequency, which depends on the density of matter in the solar neighborhood, which we take to be 0.15 solar masses per cubic parsec. Okay, so you can write down these perturbation equations, and the point is that if sine of 2 omega, where omega is the argument of perihelion, is negative, then both the perihelion and the inclination increase. Okay, and it turns out that for galactic perturbations, the rates are proportional to this. So it's actually inversely proportional to the mean motion of the comet. And that just coincidentally, all the perturbation equations on the last slide, they all go as this nu squared over n. So the time scale goes as n over nu squared. And that just turns out to be the age of the solar system at 3000 AU, and decreases with, gets shorter as you go further out. Okay, so now I'm going to show you a few figures, just assuming some parameters. So I'm assuming that things got scattered out in the ecliptic. So that means you have a inclination to the galaxy of 60 degrees. So I'll just show you a few evolutions to try to explain what this spiral is. So I've got two orbits here, both with perihelion of 30 AU, one semi-major axis of 3,000, one of 10,000. And you can see for the orbit with, you can see for both of them, the inclination rises to a value close to 90 degrees. This is integrated over 4.5 billion years. Okay, and you can see that for the closer in one, the 3000 AU, it doesn't even complete one precession cycle in 4.5 billion years. And again, this is perihelion distance. So the one with A of 10,000 AU completes a couple of cycles, and the inner one does not even complete one full cycle. And similarly with inclination. So you spend most of your time at high inclination, and then the one at 10,000 AU has a couple of episodes where the inclination gets low, or relatively low, and the perihelion actually gets into the region of the planets. Okay, so this is my only joke, but so just to show that, by comparison to the, orbit at 3,000 AU, the thing at 10,000 AU is just zipping along like a cheetah. Okay, so so in the plots I showed thus far, I assumed you started with an argument of perihelion that made the orbits, that made the perihelion and inclination go up. If instead you start with argument of perihelion in these ranges, the perihelion is initially going to go down, and then you get into this region where you're going to cross the orbits of the planets, and you're probably going to get scattered out pretty quickly. So, okay, so here's a figure from our paper trying to summarize this evolution, that you start out basically at the star, you evolve up in inclination to values near 90 degrees, and the longitude of ascending node in the galactic frame regresses a little bit. Okay, so we just implemented a simple analytic model, just considering the perturbations from the galactic disk. So our starting conditions are here. These green dots, and this is what you end up with after 4.5 billion years. So you get a clustering of things with arguments of perihelion in this range and this range, because these are the ones that evolve outward in perihelion distance. And similarly, this is eccentricity versus argument of perihelion. So you can see, so to survive, you want lower eccentricities. So a lot of them have evolved to lower eccentricities. And so if you just project our analytic model in the same way as our more detailed simulation, you get this. So you basically get similar structure. This is the full numerical simulation that has passing stars in it. So it's basically the same structure, just sort of smeared out. Okay, so is there any prospect of actually detecting this? Maybe. So we have two Sedna-like objects with semi-major axes of about 1,000 AU. That's not quite big enough to see this, because the precession is so slow there that basically nothing has happened due to the galaxy. So if LSST or some other observatory can find bodies like this with large perihelion distances and semi-major axes of a few thousand AU, we might actually see this clustering. Another possibility is you might be able to see it in thermal emission. if you assume that the inner Oort cloud has a lot of dust, and honestly, I have no idea how much dust should be there, but it's potentially observable in Planck data at their longer wavelengths. So just to summarize, here's a link to our paper, which came out recently. So we predict that the inner Oort cloud should have this long-lived and warped spiral structure. It's due to preferred ranges of argument of perihelion of bodies in the inner Oort cloud, and it might be detectable by LSST or in thermal emission. Thank you very much.
Questions?
Everybody wants lunch or fika or something.
Oh, this is a cool paper.
Hi, it's Bryce Boland from Eureka Science. So I'm pretty intrigued by the prospects of detecting these objects at, let's say, hundreds of microns wavelength. Have the cosmologists reported any anomalies? They talk about these anomalies in the microwave background. Are there any anomalies that could be consistent with, say, an excess of micron-sized dust and this orientation that you talk about with this spiral structure?
Right. So there's definitely no detection. I mean, there is a longstanding issue in the cosmic microwave background that the quadrupole seems to be smaller than predicted. And this would actually potentially explain that, because it turns out that where this emission would peak is sort of anti-aligned with the cosmic microwave background quadrupole. So it would potentially cancel out part of that and explain the anomaly. But as I understand it, there's some dispute in the cosmology community about whether this the smaller than expected quadrupole is real or not. So we've talked to some cosmologists about this, but it's not very well understood yet. Hi.
Hello. Yes. Fernando from the University of the Republic, Montevideo. That is, I'm going to talk about comet showers, and then one result is that you have a close star encounter within the inner core every 30 million years or so. This is in the region inside 10,000 astronomical units. The question is, with so many star encounters during the solar system lifetime, whether they would destroy this spiral structure.
Yeah, well, let me go back a second. I mean, so that's what this was intended to illustrate. So this is what you get if there are no stellar encounters, and this is what you get if we have stellar encounters. Now this is just a sort of a random prescription for stars of different masses and impact parameters going through the solar system, for 4.5 billion years. So, I mean, it's certainly possible that if you had a very recent close encounter, it would smear this out or destroy this, but we haven't looked at that in detail.
And Gustav, we have heard about stellar encounters and galactic tides. What could be effects of passing giant molecular clouds?
Yeah, that's a good question. We've never really modeled giant molecular clouds, and let me know what you think, Hal. But I mean, I've never been sure that we can really accurately represent the structure of giant molecular clouds well enough to model them in a meaningful way.
Martin Duncan tried this 20 years ago and never published it on its effects. And it depends on what you assume of the central density and the fractal dimension and all those things, right? And you have to push it pretty hard, I think, to actually make a big difference.
Hal, I think it looks like there's some looks like Tom has a question for Meg.
Tom Quinn, University of Washington. Just a comment on that. The other unknown is, what is the pattern speed locally in the Milky Way? Because that'll determine the frequency by which spiral molecular clouds come through, and we're probably at like co-rotation with the spiral arms, which means not very long.
Although that's probably changed over the history of the sun.
Yes.
Meg had a question.
Yeah, Meg Schwamb, Queens and Elizabeth. So I see the spiral this way. If we're maybe only going to find one or two, how are we going to know that it's in the spiral? As an observer, I'm just going to plot A, I, Q. Right? How is it that we're going to point this out rather than it's like hiding there and we all don't notice? So I'm just wondering, is this something like you easily spots sort of in the combination to put my object on top of it and go, there, that's interesting. I should go talk to Luke.
I mean, it's basically going to be preferred ranges of argument of perihelion.
Mm-hmm.
Galactic argument of perihelion.
Yeah, galactic argument of perihelion. Yeah.
None of us calculate that as observers.
But it should be both.
Right, so I'm wondering if someone's got to monitor this for us.
Pedro Lacerda, University of Coimbra. Stupid question. If you rotate this by 90 degrees, how does it look like? So if you see it from the galactic plane, from the perpendicular to the line of the intersection of these two planes.
Yeah, so it's going to be kind of warped because the inclination is going to depend on the semi-major axis. So you'd still see it. I mean, I'm not sure you'd see a spiral, but you'd see a warp.
Well, the way to think about this is that these particles are coming out at this angle.
Right.
And they hit a place where they start to precess due to the galactic tides. But you're in a regime where the timescale for that is longer than the age of the galaxy. Well, so you're just seeing this population start rotating up.
So looking at it face on, you'd see probably bands then of concentrations of things. Well,
because it
on
when the perihelion are small.
Right.
So,
Okay.
But that's really what you're seeing here.
Okay.
Yes.
Elishevah from Kooten, Globe Institute, Copenhagen. I was wondering if we can approach this by maybe probing for Oort clouds in other stellar systems, if these things exist. And
yeah, I mean,
from the outside.
In principle, you should be able to see this in other systems, and you get, unless the plane of that solar system and the galactic plane are pretty well lined, you should get this as a general phenomenon. So yeah.
Okay, so welcome back to the afternoon session. So we continue, and the first talk of the afternoon will be given by Elishevah van Kooten on the nucleosynthetic isotopic anomalies of comets.
Thank you, Morbi. So after all the nice talks about dynamic nature of the Oort cloud in the morning, I'm going to give you a light after lunch intermezzo about the chemical nature of the Oort cloud. Because I'm a cosmochemist, I'm not an astronomer or an astrophysicist. So why do cosmochemists want to know about the Oort cloud? And that's because when we take our data that we gather from different kinds of meteorites, cosmochemists tend to use the same sort of data sets. But because we are limited by the meteorites that we have, we can think of very different models to interpret these different data sets. And that will also lead to different predictions of how comets look like chemically. So here you can just see two examples of these different models on the left side and a different model on the right side. I won't go into detail, just to show you here that these models are very different. And these models are mainly based on what we call nucleosynthetic isotope data. So we have different isotope variations in the solar system, as you can see here, an example from titanium isotopes. You can see all the solar system materials that we have along a gradient line here. And we can divide these solar system materials into different reservoirs. So we would have the inner disk reservoir, the outer disk reservoir, and then we have the very innermost disk reservoir. And as you can see, these reservoirs don't line up into a nice gradient where, for example, as we go outwards in the solar system, we increase our titanium isotope ratios, but they are sort of mismatched. And one of the ways to explain this is that we can start off with a CI chondrite composition. So CI chondrites represent the solar composition. Here you can see examples of those. Bennu and Ryugu are CI-like asteroids. And in one of these models, we think that we start off with a CI chondrite composition, and then we thermally process this material, and we thermally process two different dust populations, and then end up with two different components that in the end form the very innermost solar system and the inner disk. But you can also explain this in different ways. This is a slightly different plot, but just to highlight a different model, we can also start off with an initial disk composition that's not CI-like, but it's what we call CAI-like. That stands for the most refractory solids in our solar system, the calcium aluminum inclusions. And in this model, we start off with this CAI-like reservoir, but then through late infall, we form the inner disk, and then if we mix these two components, we end up with the outer disk. So these different models lead to different predictions of what the cometary reservoir should look like. The problem with these models, just to highlight here, sorry, that we have this, in the second model, we have this gap, as you may know of, the NC and the CC dichotomy from the famous Cairo et al. Paper, a review paper, showing that this gap might have been formed by the presence of Jupiter. So with these models, we're very limited because through meteorite analysis, we're only sampling the asteroid belt, basically, which is over here. And I just put on some predictions or estimations of different masses of the asteroid belts with very low mass, and then the Oort cloud, which is supposed to have a very much higher mass. So if we could sample the Oort cloud, we would have some verification or validation of one over the other model. So that would be very nice. The difficulty was always that we thought of the asteroid belt materials and the Oort cloud materials as two very different components. So the Oort cloud, the comets, were more like dirty snowballs, whereas meteorites from the asteroid belts were more refractory materials, as you can see left up here. So they're more rocky materials. So we didn't really have access to comets. But more recently, we have a more nuanced view of asteroids and comets. They are more closely together. They more likely form a continuum rather than a dichotomy. And this is because we observe things like active asteroids in the asteroid belt, so asteroids that have tails. We find refractory inclusions in comets, as you can see down here. We have things like these CAI-like inclusions that we found from the Stardust mission, this mission where we actually sampled cometary material. And we even have chondrules. So we might be able to actually sample this cometary material. One way to do that is to look, for example, at interplanetary dust particles. So the zodiacal cloud, for example, was briefly mentioned. And these are very tiny particles, about 50 micrometers in size, and most of them we think are actually derived from comets. The problem in doing isotope work on these tiny particles is that they're simply too small to get accurate analysis of them. So we need to find a different way to get access to this cometary material. So then we can ask ourselves the question, what would a cometary nucleus look like? What are we actually looking for if we try to look for cometary material within our meteorite collection? So we sort of made a list of this to try to identify this cometary material, and we came up with a few different things, such as that this material should have a solar CI-like composition, so it shouldn't be thermally processed, it shouldn't have lost volatile materials, it should have a high ice and organic versus rock ratio, it should have this ISM signature where you would have deuterium and 50 nitrogen enrichments in organic matter. It probably has a 16O pore bulk composition, and that's based on the self-shielding model where the outer solar system, the outer disk, would be more 16O pore than the inner disk. And then we would expect to find GEMS-like structures. And these GEMS-like materials, this stands for glassy embedded metal and sulfides. These are these glassy silicates and sulfides and metal, which we think represents the precursor dust that was present in the protoplanetary disk. So this is dust that has not been altered by any secondary process on an asteroidal body. And since we don't expect comets to be altered by the interaction of water and rock, we think that we should observe a lot of these gems-like materials in cometary material. So then, when we started looking for this cometary material, we picked metal-rich carbonaceous chondrites. And these are carbonaceous chondrites, so outer disk asteroids that we think accreted relatively late and relatively far out. And the nice thing about these objects is that they contain what we call dark clasts. So you can see these dark pebble-like inclusions. And these are very volatile and organic rich. So we think these are sort of fossilized icy pebbles from the outer solar system. So these were the objects we started probing. Here you can see an example in what we call backscattered electron images up there of these clasts. And what you can see is that these clasts, they consist of very fine-grained dust, and they only contain a few of these chondrules, so less than 10 volume% of chondrules. And when we look at the overall chemical compositions of these clasts, you can see here a large range of elements according to their 50% condensation temperature. You can see that these dark clasts match the composition of CI chondrites and Ryugu pretty well. And down here in these lines, you can see other types of carbonaceous chondrites that are more volatile depleted. So these dark clasts have not lost any of their volatiles through thermal processing. Here you can see a nanoscale image. So we slice these clasts up into very thin slices, and then we could probe them through what we call transmission electron microscopy. So we can look at the nanoscale, what this fine-grained material is made of. And what you can see in there when you look at what these pink arrows are all pointing to is these gems-like structures that I talked about before. In white, you can see all these tiny sulfides. And in between, we have this glassy silicate material, also interspersed with a lot of organic material. So we call these structures organosulfide complexes. And when we look into detail at this white stuff here, this is another image where the white stuff actually represents organic material rather than the sulfides. When we look into detail at the structure of this organic material that we find, we can sort of analyze the different functional groups inside of this organic matter, and we can compare it to the organic structure of cometary IDPs. So that's from a paper from Henner Buseman in 2009. He showed the structure of organic matter in cometary IDPs, and this resembles the organic matter in our dark clasts to a very high degree. We also measured the oxygen isotope compositions of these clasts, and you can see here compared to a cometary IDP again, and to another class that also is proposed to be cometary, and you can see that we have sampled some of the most 16O pore material that we found so far in our meteorite collection. The only more 16O pore material that we have found is from hotspots that we find in cometary IDPs. So this is a bit more complicated plot, so I'll just go through it a bit slower. Here you can see the nitrogen isotope values on the y-axis. Oh, no, I'm going to look there, but I should look here. And then on the x-axis, you can see the D/H ratio, or the delta D value. And just for the astronomers in the room who are more used to looking at ratios rather than delta notations, you can see up here the ratios of these two different axes. So when we look at solar system materials in hydrogen versus nitrogen isotope space, we can identify two main components that together form the bulk of these materials. One component is the organic matter, which lies along a line over here. This is thought to be an ISM signature of refractory organic matter found in chondrites. And then over here on this, in this blue bar, you can see the composition measured or inferred for the water ice component in these chondrites. So if you mix these two together, the organics and the ice component, you get the bulk composition, which you can see here. So you can see in purple a lot of the carbonaceous chondrites, and you can see a lot of cometary IDPs. And then when we plot these dark clasts in there, you can see here the bulk value, which is very 50 nitrogen rich. you can see the carbon-rich component, and you can see the organic matter component of these clasts, and together they all fall along this mixing line over here. And you can see that we're mixing in organic material, which is very 50 nitrogen and deuterium rich over here, and we're mixing that with an ice component that is also very 50 nitrogen rich compared to the ice component that we find for other carbonaceous chondrites. So this 50 nitrogen rich signature is a clear outer disk signature, and we have a clear ISM signature, so we think that materials falling along this line are cometary materials rather than the carbonaceous chondrites which formed a bit more closer sunwards. Then one nice thing we can do is we can try to quantify this a bit more to see what the ice versus organic ratio is here for these dark clasts, and we can calculate that we have 60 versus 40% of ice to organic matter. Then if we try to infer the organic versus rock ratio of that, we can look again at our TEM or transmission electron microscopy images, and we can plot our dark clasts in this diagram over here, which is a ternary diagram where you can see the ice, organic, and silicate component. And you can see this range of solar system materials, where down here we have the asteroids, and when you go up there, you get more ice and organic rich, and you start to go towards the comets. When we plot our dark clasts in there, you can see these yellow spheres. They plot most closely to a cometary composition. So all of this together was good evidence for us that we were looking at materials that are the closest to comets as we can come in our meteorite collection. So then the nice thing is that these clasts, in contrast to the IDPs that I was talking about, are actually millimeter sized, and those are big enough for us to measure the nucleosynthetic isotope anomalies of these materials. So then we can finally use these materials to verify which model we think is true for the formation of our solar system. So one of the ideas, fairly recently actually in 2022, is based on the analysis that people did on Ryugu samples and now also on Bennu samples, is that these CI chondrites form sort of a separate reservoir from the other carbonaceous chondrites. And then people were thinking that because of that, these CI chondrites and Ryugu and Bennu must have formed in the outermost solar system and would represent comets best. But if we plot the composition of our dark clasts in there, I'm just going to call them odds for outer disk dark clasts, you can see that they don't plot at the CI chondrites at all. They plot all the way up here. So that means to us that if odds represent the cometary composition, then CI chondrites are not good representatives of the cometary reservoir. Another analysis that we did is for silicon and iron isotope analysis. And here we could, for the first time, see that these dark clasts represent an end member of the composition of the outer disk. So if this is all the outer disk materials that we have, so these are all carbonaceous chondrites, they are mixed by two end members, namely the dark class that we have here and CI chondrites down in here. And this would represent the inner solar system. So we have a trichotomy where we have a cometary reservoir, CI-like reservoir, and an innermost reservoir. And so this paper came out last year, and one of the things that I've been trying to do in the last few years is try to verify this outer disk mixing lines by looking at more samples than we have, and this is by looking at what we call ungrouped chondrites. So we have a lot of classified chondrites, so we can put them in specific groups based on their oxygen isotope compositions, but also on their petrography. So I'll put it up here as just to show you what that is. The size and distribution of chondrules and matrix, that sort of thing. So that makes up the petrography. And if this petrography or oxygen isotope composition or both does not measure up to any known classified chondrite group, then we would call them ungrouped. And we can use these materials to probe the outer disk in more detail. Just to show you that. So then we try to measure all the main rock-forming elements and their isotope systematics, silicon, iron, and magnesium. And I'm showing you the same plot here that I showed you before, just with a lot more data on there. And you can see that all these ungrouped chondrites, which are these small green dots over here, they match the same mixing line as these grouped CCs that you see over here. So this sort of verifies this mixing line of two different components in the outer disk. Now we can do the same for magnesium versus silicon isotopes. And again, you can see this outer disk trend where you mix cometary material with CI-like material to form the disk. So just neglecting the inner solar system for a moment, we can say all outer disk materials are a mixture isotopically between a CI-like and cometary material. So then how would this have happened dynamically or physically? How do we get from an initially CI-like disk polluting the outer disk with fresh material? So one way to do that is through streamers or accretionary filaments, where protoplanetary disks are not just fed by infall from their envelope, but they can be fed by parsec scale accretionary filaments that are not homogeneous on that scale, but it can be heterogeneous on an isotope scale. And this we know through both observations and models. So instead of the normal view of solar system formation that you usually see as the solar system as an isolated sphere that collapses and forms a disk, the solar system actually looks like a filamentary structure where you feed the disk continuously through different types of filaments that can bring in this fresh dust. So if we summarize that all together, the material that now makes up the Oort cloud was initially formed in the protoplanetary disk through a streamer adding fresh material to the disk. Thank you.
Questions? To clarify, so this late material should be the CI or the cometary material?
The cometary
material.
Yes.
Would be added to a disk that is initially CI?
Yes.
Okay. And the CAIs out of this, how do you place them?
The CAIs, we think, are formed because they are very enriched in certain isotope systematics, and we think that they formed from a gas that was thermally processed. So you thermally process CI-like material, you form a gas that is very enriched isotopically, and then you condense that.
Pedro?
Pedro from the University of Coimbra. The Stardust mission at that time was quite surprising because it showed that an object that is distant had material that had been very hot, very close to the sun, and so the degree of mixing in the disk must have been much bigger than what people thought at that time. Is this streamer a way to explain that? That basically the streamer sort of sprinkles? No, because that's not... That's the opposite, right?
Yeah, well, the streamer could potentially do a lot of things. The streamer could add fresh material, but it could also sort of kickstart different processes. It could start a new range of planetesimal formation. It could maybe even be responsible for chondral formation. So instead of having chondrals, like these high temperature components that you were talking about, moving from the inner disk to the outer disk, you can have chondral formation locally in place. So you don't need to have that kind of transport over there.
I see. And I have one more question. So what's the origin of the streamer? So the direction, the concentration?
We don't know. This is a question we're trying to answer also with people that model these kinds of streamers. Where would we expect these kind of streamers to be attached to the disk? Is this more likely to happen in the outer disk, as we would expect from this data? Or can this also happen in the inner disk? And how local is this? So, and at what time would you expect these streamers to come in? So these are a lot of unanswered questions. But now that we have this data, we sort of know the process that must have happened. We just need to constrain it further.
And Gustafsson, in this complex and interesting picture, what do you consider to be the most representative chemical composition of your different mixtures here for the pre-solar nebula, if it were unmixed, or if it was mixed?
I think that the initial composition of the solar nebula must have been like Ryugu and Bennu, like CI chondrite material. Yes. And chemically, comets are the same, just isotopically, they're different. Yeah.
Hal Levison from Southwest, Boulder. I'd like to understand the timing of all this, right? So you can get ages for these chondrites. Right?
Yes.
Is it possible to look at correlations between the isotopic ratios and timing to try to figure out when this material was added to the solar system? Do you have any constraints on that?
Yeah, so some of these chondrites where we identified these dark classes in, we have chondral ages. So we know when the first materials that formed these chondrites formed. And these were formed about 2 million years after the first solids formed. So if we have to place any timing on when these streamers came in, it has to be somewhere after the first 1 or 2 million years.
More questions?
Hey, Anders Johansen from University of Copenhagen, one of your colleagues. I was just wondering, you're saying these IDPs are too small for isotopic measurement. Can you take 1,000 of them and measure together, or would that give a meaningless answer somehow?
Sure, we could try to do that. This is actually one of the things we're working on right now. We're trying to measure individual micrometeorites. So those are IDPs that entered through Earth's atmosphere and have been molten. And we're getting the first data on these micrometeorites now. And the next step is to downscale this even more to the IDPs. So these micrometeorites, they have fairly large sizes. They're maybe 300 micrometers in diameter. And then we have to go down to 100 or 50 micrometer. But we're slowly getting there. We're getting better and better in measuring these things.
Yeah. Yeah, Julio Fernandez. My question is quite speculative. That is the solar system formed in an open cluster. Will it be possible to observe these kind of streamers in other open clusters that we are currently observing? Because what happened in the solar system should occur right now in other stellar clusters, where stars just are capturing streamers from the neighborhood.
Yes, there are plenty of observations right now on different streamers to other protoplanetary disks. I'm not certain in what type of dense or open cluster they are, but people are being more aware that this is a common thing happening to a disk rather than a rare thing.
Another question?
Well, I was going to ask a similar question about observations and other. I know it's not your field, but there was work by Henry Throop and John Bally years and years ago about secondary accretion events onto disks as they move through star-forming regions. I've been following the field since then. But can you comment about the observations? Is it consistent with your time scale? How much would you expect the chemistry of the material falling around to be different?
Well, we noticed from an isotopic perspective, I don't know if you know the Kufmeyer papers, that they look at parsec scales of giant molecular clouds, and they can see that throughout this cloud you have very heterogeneous compositions of materials. So you can add materials that are isotopically completely different. Chemically, I don't think this has been modeled yet. There are observations, but they don't really trace the rock-forming elements, more different light element gases like HCN or ammonia or these type of gases.
So these are materials that formed, but these are materials that formed from the same giant molecular cloud, right?
Yes.
So why do you see large-scale differences?
Well, because you continue to have stellar contributions, nucleosynthesis from different types of objects that can pollute the cloud, right?
So this is second-generation material that has come off in stellar winds and things like that.
Yeah.
Okay.
Yeah.
That's cool.
Final one, if I may. The solar system is extremely coplanar, right? The cold Kuiper belt, which is sort of untouched by planetary perturbation, it just has a dispersion of a few degrees over the midplane of the solar system. And when streamers come, they come with a random orientation, of course. So is it consistent with having such a huge coplanarity throughout the cometary disk?
Well, throughout part of the cometary disk, right?
No, it's the entire cometary disk, because the Kuiper belt is actually we don't get comets from the cold Kuiper belt, actually. So it's beyond the disk that was dispersed to go in the scattered disk and the Oort cloud. So it's really the outer edge of the planetesimal disk total, right? Would you agree about that? Anderson, sorry, the final bit of the planetesimal disk, they call the Kuiper belt. So everything looks extremely coplanar. So of course it does not exclude the streamer if by chance the streamer had the same orientation, or the streamer came in early enough that the disk could dewarp. So do you have thoughts in the group about that?
Well, it's also dependent on how much mass the streamer can contribute, I think.
Sure.
And it's according to models and observations, it's suggested that this mass can be at least the size of the initial disk mass. So I would assume that if you have this much mass replenishing the disk, you can actually form a whole new disk with everything falling on the same plane. But that's outside of my field.
I'll remind you, Morby, that the disk is inclined with respect to the sun's equator.
Yeah, by 60 degrees. But it's a whole disk.
You could jump. If the whole thing just
there is no warping. There is no warping.
There's no warp.
That's what I'm.
How much stuff can you put on the pizza without disturbing the shape of the pizza?
Yeah, exactly. Okay, thank you. Thanks Elishevah again. The next talk is given by Sławomir Breiter, and he goes back to a more traditional topic, which is the role of the galactic tide in Oort cloud dynamics.
No title slide.
You will go beyond the presentation. Okay, this is it. Go forward. Not back.
Okay. So I have to move forward, and I have to introduce myself in this case. I'm Sławomir Breiter and in spite of my first name, I'm not from Gondor, I'm from Poznań, Poland. And now I want to show you how it works. Forwards, yeah, backwards. That's what I did, exactly. Exactly, and with the same result.
So it was on purpose. Okay.
So, I'm from Poznań, Poland, and since I'm about to speak of the galaxy action on Oort cloud comets, so every respectable speaker from this conference who speaks about the dynamics of comets inevitably speaks about the action of the galaxy. So what can I add to the topic, not being active in the field for a couple of years? Well, if I cannot add, I can subtract. And I will subtract, and I will present you, well, the preliminary introduction to the basics of the fundamentals of the galactic tide action on comets, which means rather lack of details, and the story, for example, will not contain any mention of planets. No planets allowed, so it means I will never mention the ecliptic, and I will always speak about the galactic plane, and the motion will be considered heliocentric. And so the story is about how the galaxy affects the, affects the Oort cloud. You see this picture for the next time, and you will see it many times in this conference, I think. And when we come back to the story of Oort, who proposed the Oort cloud, now is called, in 1950s, he discarded galaxy. He only was speaking about some passing stars, and this is the only mechanism that matters according to Oort. So there's a Polish proverb about the barefoot shoemaker, Oort, master of the galaxy, discarded galaxy, only was considering some passing stars that throw in the comets from the Oort cloud into the solar system. Nowadays, we speak about basically two phenomena: the joint action of the galaxy, which is systematic, and the passing stars or molecular crowds, which act sporadically. So the only systematic phenomenon, once we leave aside the planets, is the action of the galaxy. Now, technically, the passing stars are also a part of galaxy, just like the sun and the comets, but I will use the term galaxy for a bulk system of stars. Sometimes some stars will be detached from the galaxy. Now, what is this business with galactic tide? First of all, remind you it's differential acceleration. If you start thinking about the force acting on the sun attracted by the galaxy and force acting on a comet attracted by the galaxy, then you may have funny conclusions because they are strikingly different, but the accelerations are quite similar when you compare them. Since the action of galaxy is at two distinct points, you will have something that have a differential acceleration, what is called tide. Of course, galaxy is not drawn because this whole system is embedded in the galaxy. And so whenever you hear about the tidal force, it's understood as differential or residual acceleration times the comet's mass. But in practice, nobody multiplies it by the comet's mass, and it's meant force per unit mass. Whoever speaks about the force, tidal force, it's force per unit mass, hence acceleration. And it's, in this context, is a force of inertia, so-called. It's not a physical force, because it's related to the motion of the reference frame, the sun in this case. Now I will distinguish two kinds of the galactic tides, direct and indirect. Direct is the one when the comet is perturbed by the galactic field. Now, indirect is when you have a passing star which is also attracted by the galaxy, and if you think in heliocentric terms, the star also is acted by the galactic tide, and disturbing the motion of a comet, it acts as indirect galactic tide. Now, who brought the galactic tide to the cometary considerations? Since Oort didn't do it, there were early attempts by Van Flandern and Bill in 1977 and 83. You have the titles of the papers to indicate that what Van Flandern wrote was actually to show that it makes no point in introducing the galactic tide, because he was mostly concerned with demonstrating that some major planet of the solar system does the job. And these early attempts were focusing only on the galactic center, so they were using the circular restricted three-body problem, which is not a good solution. So the modern era of using the galactic tide comes with Heisler and Tremaine in 1986, and Bill in the same year, but Bill was a bit later, so I consider Heisler and Tremaine as the fundamental initial publication. Now, the problem is Hamiltonian, because the action is gravitational in principle, or the forces of inertia, which also can be written in a Hamiltonian form. We can distinguish the Kepler part, where you have the momenta per mass, which means velocities in practice. So there's kinetic energy and the Keplerian term with x, y, z coordinates, heliocentric. Reference frame is heliocentric. The OXY plane is parallel to the galactic plane. Sometimes it's rotating. Okay, and now mu parameter, let's say it's 4 × 10⁴ for the reference. And there may be possibility to introduce 3 levels of the galactic tides modeling. I skipped the circular restricted three-body problem as a wrong track. So effectively, we in practice model the galactic tides using 3 levels of approximation. The first one is galactic disk tides. I will call it level 1. So only galactic disk is taken into account. The second is galactic disk and center tides. So it is still somehow simplified model. And the third is taking the complete galactic potential tides. Noteworthy, whenever you speak about the tidal force in L1, L2 model, it's actually the linear approximation of the acceleration, which means that the tidal potential is a quadratic form in coordinates. Whereas the complete galactic potential tides should use nonlinear approximation of exact formulation of the galactic potential. Thus, to make the brief account, level L1 is the disk. You see that the Hamiltonian, the perturbing Hamiltonian, contains only the square in z coordinate, and compared to 10 to 4, you have this G3 potential 10 to minus 3. Then, if you move to the levels 2, you have now not only a tail, but a head and a tail, and the potential is taken in a rotating reference frame, rotating, well, heliocentric, rotating with the angular velocity of the sun traveling around the galaxy. So you have, again, the quadratic form, but there are terms with G2 and omega 0, where G2 is 10 to minus 4. You see it's something like 10 times smaller than the disk-related coefficient, and this rotation rate is the square root of G2. So now comes the complete model, and there you see it's more sophisticated and more realistic and more dangerous than L1 and L2, but if you charm it sufficiently, you can use it. So really, without a figurative, it's now the potential which is represented, for example, as a sum of 3 terms, one related to the bulge, one related to the disk, and one related to the halo. And you should use all 3 of them instead to have a complete level 3 approximation. Now, level 1. Well, while looking at some publications by Scott Tremaine, I found a paper titled, Why is the Galactic Disk So Cool? And my first impression was that we think about the same thing, but no, they thought really about the temperature of the galactic disk, whereas I was thinking that galactic disk is really cool, man. Yeah. And I will show you why. Because it's the model that has rotational symmetry with respect to z-axis. It's time independent. So we have 2 integrals in the Hamiltonian system. The complete energy, the Hamiltonian function, is constant, and the z component of the angular momentum is also constant. So it's a 2 degrees of freedom system. Maciejewski and Prędka in 1998 derived lower bounds on the heliocentric distance for these 2 constants given, which is a very useful result. And it has some very fancy features like the perturbation vanishing at some points during the motion. You know, since whenever a comet crosses z equals 0 plane, its motion is exactly Keplerian because there's no perturbation, which means that whenever a comet passes the galactic plane, it has exactly the same semi-major axis. Whatever happens between these 2 points, the crossing of the galactic plane is always with the same semi-major axis. Now, the standard perturbation methods allow the removal of the mean anomaly, which means that you can drop 1 degree of freedom and you obtain 1 degree of freedom system with prime integrals. Mean semi-axis is constant. The z component of the angular momentum when scaled is constant. And the new Hamiltonian averaged one is constant. So the normalized Hamiltonian can be expressed in terms of the angular momentum and eccentricity vector to have such a nice form. You see it's actually quadratic form in components of angular momentum, h1, h2, and the third component of the Laplace or eccentricity vector. Very simple representation. And complete solution of this averaged problem has been elaborated, well, between 1989 and 2007. I quote 3 basic papers where the solution has been obtained. It's in terms of elliptic functions and elliptic integrals. So it's a nice solution because everyone loves elliptic functions. And now, if you look at this, at one of these integrals that I mentioned, the mean 1 minus square of eccentricity times cosine of inclination, the z component of the angular momentum, you see that we have a trade-off between eccentricity and inclination, which means that in order to fuel the growth of eccentricity, you have to take high inclination. Yeah? Highly inclined orbit with small eccentricity will evolve into small inclination orbit with high eccentricity. And that's the basic mechanism which is typical for the von Zeipel-Kozai-Lidov phenomena. But don't be misled, the story is also, and even more, about the latitude of perihelion than about the orbital plane inclination, because libration and circulation of the Laplace vector, of the tip of the eccentricity vector, can be explained by intersecting the surfaces of 2 prime integrals in the reference frame attached to the ascending node, as we did in a paper from 1996. So we consider 2 surfaces obtained as graphs of constant new averaged Hamiltonian, and it's this one when expressed in terms of Laplace vector only, and the z component of the angular momentum, which can also be expressed in terms of the eccentricity vector components. Now, if you plot these surfaces, for example, you find, depending on the sign of beta, you have either a hyperboloid of revolution with 1 sheet where the tip of the Laplace vector must be located, or you have a hyperboloid of 2 sheets where the tip of the Laplace vector should be contained. And then you intersect them with the red surface, which is z angular momentum component constant, which is written in this nodal frame, and it's this one 2-lobed structure. Now, if you intersect it with the hyperboloid of 1 sheet, you have these curves along which the eccentricity vector evolves. So this is a phenomenon which is related to the circulation on this typical plot where you have the argument of perihelion and eccentricity. But see that whenever the inclination is at maximum, the latitude of the Laplace vector is at minimum. And if you take the case where you have the hyperboloid of 2 sheets, then the evolution of the eccentricity vector is along any of these 4 curves. And once again, the highest, the inclination of the line of the apsidis, or latitude of the Laplace vector. Whenever it's maximum, the eccentricity is the greatest. But the greatest eccentricity means the smallest inclination. Yeah? So it's more the story about the latitude of the Laplace vector than about the inclination of the orbit. So this phenomenon has much of similarity with the von Zeipel-Lidov-Kozai resonance, as I told. It has stationary points of the averaged system, which refer to the periodic orbits in the original 2 degrees of freedom system. They appear when the line of apsides is perpendicular to the line of nodes, which means argument of perihelion 90 degrees or 270 degrees. The eccentricity must have this specific value depending on the constants alpha, beta, and inclination. Also, like this, and the latitude of perihelion is also given in terms of these two fundamental quantities. Strictly speaking, the problem is non-integrable. But one starts to feel it far beyond the Oort cloud. For example, if you see a plot from Maciejewski and Prędka, you see the scale is 10,000 AU as a unit, so it's 100,000, 200,000, and so on, to feel the chaotic motion on a Poincaré surface of section. If you want the fresh applications of the non-integrable integrable approximation of the average system, you can refer to the paper just presented by about the spiral structures in the Oort cloud. Now let's move to the level 2. In the level 2, we fix one of the axes to point to the sun center line. So we retain a time-independent Hamiltonian, but the OZ axis symmetry no longer exists because we lose the rotation symmetry around the OZ axis. And in the galactic plane Z0, the perturbation does not disappear, only this term disappears. But then we have exactly the Hill problem, which is a case of the circular three-body problem with a very, very distant second body. Otherwise, if Z is not 0, we can think about the perturbed Hill problem because it has a different Z coefficient than the original Hill problem. So we are at the 3 degrees of freedom. Even if we remove mean anomaly by normalization, we will have a non-integrable 2 degrees of freedom problem. Hence, the possibility of a second normalization formally exists, but has not been yet explored to my knowledge. It is possible formally to attack the problem after first normalization, to remove further 1 degree of freedom, taking care about possible resonances, but no one yet done it. Now, if we are using this averaged system, rewritten in this form in terms of the eccentricity vector and angular momentum vector coordinates, with the parameter nu, which is the measure of ratio of the disk-related coefficient to the center, the related coefficient, roughly speaking, it's 0.125, as I mentioned. The analysis of this case was, for example, done with Marc Fouchard and Roman Ratajczak in 2007. We searched for stationary points and did numerical integration. But it turned out that almost all interesting phenomena, like bifurcations or the origins of chaos, are practically at the outskirts of the Oort cloud. It is at least 50,000 AU. Here's an example of a map of so-called Magno coefficient that distinguishes the regular and chaotic motion. You see that in thousands of AU, you have to go at least to 50, 70,000 AU to observe the major chaotic zones and to see that there are some periodic orbits with bifurcation, which is resulting in such fancy plots, probably known to anyone who does analysis of nonlinear systems. Anyway, to sum up, the widespread opinion is that adding the galactic center does not change much inside the Oort cloud in its inner parts, but of course it's unless we need an integrable approximation, it's always better to use a more realistic model. Now we come to the level 3, which means so-called real galaxy potential. For example, we can take one from Irgang et al. With the term for the bulge, the term for the disk, the term for the halo. And now what happens? You need to compute the differential approximation. So you take the gradient of this potential at the sun, you take the gradient of this potential at the comet or another body, and the heliocentric term. Okay, this is position R sun plus R plus small r. Here is the position R sun inside the galaxy, but the sun is somewhere here in the galaxy. So the differential acceleration, the galactic tide, will have this term, which is subtraction of these two gradients. And here comes the problem, because if you want to compute it directly, okay, you have to subtract such accelerations at two very near points. And when you are far in the Oort cloud, you lose 5 digits when asking computer to subtract these two numbers. But once the comet visits the solar system, you have real disaster, because actually the loss of accuracy is such that no significant digits remain. So what is the solution? Of course, you can expand in terms of the ratio of the heliocentric distance to the position of the sun in the galaxy and obtain, for example, the linear model, but this brings you to the level 2, which means that close to the sun you can use the level 2, and far from the sun you can use the more sophisticated model, but switching between such models, it's not a good habit in longer simulations and may introduce some artifacts, and it lacks some spirit, so to say. But the problem itself, it's not new. Well, I don't know if there's anyone at this hall who still remember terms like special perturbations and NK-type integration using hand arithmetic devices. But it was considered in the epoch. NK was proposed to integrate numerically not the motion of an object around the sun perturbed by planets, but to integrate numerically only the deviations from the Keplerian motion induced by planets. And this, of course, led to the problem that we subtract two close numbers, and NK himself proposed some rearrangement of the forces to have it in a better form. And the same thing was done 3 years ago in collaboration with Piotr Dybczyński. We obtained the expressions that are free from the problem of subtracting similar numbers. Very simple tricks were played, the rearrangements like this to have something that really has big number plus small number instead of subtracting two huge numbers. The level 3 is really indispensable when it comes to considering the indirect effect that I told about. It is when passing stars move in the galactic fields and we want to model them correctly. The local approximation by the models L1, L2 is here absolutely not appropriate. And if one is using the simplistic straight line approximation, and we model the swarm of the clones of a passing star, okay, we can obtain something like this using the straight line model. But if you use the L3 approximation, the complete galactic disk, so you have the full model, you may have completely different results. Not often, rarely, but it may happen. And you see with the Oort cloud radius given here, the passing star is either close enough to do something serious or not. Here is the example of two miss distance of a passing star obtained using two different galaxy models. I don't even say two approximations of the same model, but two different galactic models. So, time for conclusions. What can I say on such an elementary model? How does the galaxy affect the Oort cloud comets? Considerably. And that's all.
There are questions on this, Giovanni.
Giovanni Valsecchi from the National Institute of Astrophysics of Italy. You said at a certain point that adding the center of the galaxy doesn't change very much. Well,
that's what people say, numerically, because they spot that the coefficient related to the galactic center is 10 times smaller.
Yes,
and unless we find some situation which is far away from the sun, and there may appear some resonances related to the rotation of the reference frame, to the frequencies induced by the galactic center with, and the resonance with other phenomena. So as long as we don't meet these interesting nonlinear terms, you can say that, okay, this is enough.
Yes, because I would advocate the contrary opinion, of course, because computations that Marc Fouchard and Hans and Christian Fischler and I did show that if you just use the L1 approximation in which everything is integrable, of course you exhaust in the first 100 million, perhaps first billion years, all the comets in the Oort cloud that could become planet crossers, and then you have an empty Oort cloud, not empty of comets, but empty of comets that penetrate the solar system.
The lost cone.
And in fact, it shows that the galactic center, if you add it, you render this problem not integrable, and you add exactly what is needed to maintain the flux. That's the physical picture.
Questions, comments? Yes, Tom?
Tom Quinn, University of Washington. So, do you assume the sun is in a circular orbit around the galactic center, and does it matter if it isn't?
Well, on the level 3, strictly you should consider the motion in the galactic field. The sun moves in the galactic field under the action of the galactic field. Yeah? So that's the really grown-up model, and then you have to subtract two trajectories, the sun and the passing star, or the sun and the comet. But best is to do it, well, integrate the sun alone and then trace the rest heliocentrically.
More questions? Maybe I have one. So before in the morning we talked about the effect of the cluster, and typically the cluster often is considered like a sort of galactic tide, just strengthened up, increased by an order of magnitude or so, depending on the density of the cluster. So in your description of level 1, level 2, level 3, so how should a cluster be modeled?
Well, as a model 3+. That's the best I can say for now.
Okay. All right, so before we move to the coffee break, Sławomir has an announcement that may interest most of us.
May I ask for displaying?
Do you have a slide for that?
I asked to open
the
link.
Okay.
To certain web page.
And will be put on the screen. Here we go.
Okay,
yeah,
so as I told, I'm from Poznań, Poland, and the next year, roughly at this time, a month later, in July, we will have Asteroids, Comets, Meteors conference. You are all invited, so please find the web page under the name easy to remember, acm2026.eu. This is tricky, .eu, Europe.
Yeah, sure.
And there is indication of interest tab at the bottom of the page. Click it. Thank you. That's
Okay, thank you very much.
Okay, so it's a long-time collaboration for many years that started with Hans Rickman, Giovanni and Christian Fouchard many years ago, and now so it's with Melaine, Arika Iguchi, Takashi Ito, and Vasisla Emelianenko. And so I will speak about the dynamics, the simulation we have made. We will focus on the observable comet in our simulation, and then we will see also the memory. We can solve the memory of the initial shape of the Oort cloud in the long period comets that are observable, and then we will consider observation made now of long period comets. So we have this well-known picture, the picture that justifies our presence here, so the picture by Oort, and this, in some sense, it is the first time where looking to the orbital energy distribution of long period comets, so it has information about the the possibility of this Oort cloud. So the idea here is again to see if in the orbital distribution elements of long period comet we can retrieve some information about the Oort cloud, the present shape or eventually its initial shape. So our simulation take into account the galactic tide. It is a L2 model according to the Sławek presentation before. We will consider also passing stars and planets. So for the galactic tide, I will just introduce the approximation considering the L1 model, just because it allows to explain some general feature of the simulation. So we have here the, I will use this, okay, the lead of quasi resonance here, and this is caused by the normal the disk of the galaxy, and so we have a differential force that explains this motion. It's quasi-integrable dynamics, and we have the variation of the periodic distance scaled as a semi-major axis to the power 3.5, okay, over one orbital period. And we have also the period of one cycle here, scaled more or less as the inverse of the orbital period of the body. Okay, so it means that the further we are, the faster will be this cycle, and also the period distance will also vary much. We will have a larger perturbation in one orbital period for large semi-major axis. For passing stars, we have used here a sample of passing stars over 4 billion years. And we have 13 different stellar masses with encounter frequency based on the solar neighborhood, the actual solar neighborhoods. These statistics are constant during all our simulation. And we use this data to build our sample of, we have about, I think, 200 stellar passage within 400,000 astronomical units from the Sun in 5 billion years. For the planetary perturbation, we use a very simple model. We first model the perturbation only when the period distance is smaller than 70 astronomical units, and we make the integration, a numerical integration, only on the part of the orbit that is at less than 250 astronomical units from the Sun. And we took into account only the 4 giant planets that we consider on coplanar or circular orbit, so we don't have to worry about the integration of the planet. It's simple, but as far as the semi-major axis of the comet is large, it was a reasonable approximation. So the idea was to see, considering two different kinds of initial proto-Oort cloud. So we don't consider here the formation of the Oort cloud itself. We start with an already formed Oort cloud, but we have two different proto-Oort cloud. One which is a disk-like, that is, we have the inclination which is smaller than 20 degrees, the perihelion which is between 3 and 50 astronomical units, and well, the semi-major axis between 500 and 20,000 astronomical units. This is for the disk-like, and we have the isotopic model, where we have a fully thermalized Oort cloud with a uniform distribution of all the orbital elements, and with a period distance which is larger than 15 astronomical units in this case. The angle here is galactic inclination here, whereas here we used the ecliptic inclination. In our simulation, we first inject randomly the comet into the Oort cloud between 0 and 266 million years, which is more or less one rotation of the solar system around the galactic center. Then for about nearly 5 billion years, we propagate our sample of comets, considering the full galactic tides, well, the L2 model, the T2 model, passing stars, and planetary perturbation. At the end, we store all the comets that remained in the Oort cloud at 5 different snapshots between 3.75 and 4.75 giga-years. Then, for 30 million years, we continue the propagation, but we remove all the stars that could produce a comet shower, okay, just to be in a quiet period, just because observationally we have no indication that we are actually supporting a comet shower, okay? And then we just stop the integration at the first perihelion passage after this 13 million years relaxation period, okay? If the perihelion distance is smaller than 5 astronomical units and the semi-major axis is larger than 10,000 astronomical units, that is because we focus on what we call the new Oort cloud comets, okay, so comets that are coming into the solar system for the first time, okay. So this will be our sample of observable comets in our simulation. Okay. Yes, this is yes, the definition I use for an observable comet, a new long period comet. Okay. At the end of the process, just before the comet become observable, we have different kinds. It's a very different way to become observable. Mainly, we identify 4 different kinds of comets that are observable. We have here the perihelion distance in abscissa and the semi-major axis in the ordinate, and we have one point at each perihelion passage. The color of the point is an indication of the inclination of the ecliptic inclination of the comets. Okay, and here you see for the jumper. At the end, you have the perihelion distance that jump this gray area that corresponds to what we call the Jupiter-Saturn barrier, that was called also the lost cone before. That is, if a comet fall into this gray area, it was supposed to be ejected from the solar system, from the Oort cloud. Okay, so this is a jumper, but in fact, in the simulation, it appears that we have this Kaiban-Quinn process that was highlighted in 2009, where to be a jumper, we need a semi-major axis large enough in order to have a variation of the perihelion distance in one orbital period that allow this jump. Okay, but for a Kaiban-Quinn jumper, we see that the semi-major axis for almost all the propagation was rather low, and it was not possible to have this jump, but just at the perihelion passage, just before the observation, it supports scattering by the giant planets, mainly Neptune and Uranus, that increase the semi-major axis here, and this allows the tide to inject the comet to jump the Jupiter-Saturn barrier. Okay, this is what we call a carbon queen jumper. Okay. In the simulation, we had also some creeper that are comets that just the previous period distance fall into the Jupiter-Saturn barrier, but they were not ejected, and they just continue to have their period distance decreasing, so that at the end they are indeed observable. Okay, and we have also some carbon queen creepers that they are in the Jupiter-Saturn barrier. With you see they are with the blue points, which means that they are strongly retrograde. The inclination is very large, and this makes the planets much less efficient to eject them to affect the orbital energy. But still, that this one at the perihelion before observation supports a planetary kick, and at the end it makes the jump. Okay. So we define here the jump to be in orbital energy, a variation of this side. Okay, this is what we use to define the carbon queen process. When we look to the Oort cloud, the finite Oort cloud we obtained in our simulation for the disk model and the isotopic model, we see here you have the distribution of, I will not comment everything, but mainly the upper color histogram here, where you have here the orbital energy, the distribution of the orbital energy, and the colored area referred to the proportion of jumper for the red comet, carbon queen in orange, carbon queen creeper in magenta, and blue for creeper. Well, at the end, we don't see strong qualitative differences between the isotopic models and the disk model. In both cases, we have mainly the creepers, carbon queen or not, that are found in the inner part of the Oort peak, whereas jumper are found in the outer part of the Oort peak. Maybe the isotopic model, well, the disk model produce more prograde orbits than the isotopic one, but at the end, the main differences is in the flux of long period comets. When we scale to population of objects in the Oort cloud of 10 to the 12 objects, we have a flux of 3.8 comets per million years with period distance smaller than 5, and it's nearly 4 times less for the isotopic models. So this is just to show the simulation we performed for the isotopic model. We have here the initial condition for the isotopic model in a different plane. So you have the period distance. The axis is always the semi-major axis, and here you have the period distance, the cosine of the ecliptic inclination, the galactic argument of perihelion, and the galactic longitude of the ascending node here. So we have a uniform distribution, and the dot correspond to the comets that are at the end observable. Okay, so the red are jumper, again, orange are carbon queen jumper, magenta are carbon queen creeper, and blue are creeper. This is the initial condition, and okay, there was some animation, but never mind. This is a situation after 3.5 billion years, so just before we start to have our snapshot to see. So this is where are the comets before they become observable. Well, here we don't see a very significant structure. Maybe the only one is here. You see accumulation of the galactic argument of perihelion that are around 270 and here 45 degrees. This is a argument of perihelion for which the period distance is decreasing caused by the galactic tide. Okay, so they are on the way to the observable region. Okay, if we now look to the disk model, so these are our initial conditions. So it's a flat disk, as you can see here. Okay, and if we look at the end, what we obtain, we see here that the distribution mainly for the argument of perihelion and the galactic argument of perihelion and the galactic longitude of the ascending node, you have a strongly non-uniform distribution, and at least until 10,000 astronomical units. These are the spiral arms that Luke don't show us before. So clearly it's difficult to see a spiral here, but it's well, we checked and it's indeed the same kind of structure we had here. We see here that the carbon queen jumper are still in a kind of extended scattered disk here. So maybe it's more evident here. And the through jumper are found at the end. They are still in the outermost part of the Oort cloud. That this part is at the end fully isotropic. Okay, beyond 20,000 astronomical units, the Oort cloud at the end is fully isotropic. Okay, so to conclude for this long-term evolution, so no clear structure for the isotropic model, whereas for the disk model, we see that we have mainly the carbon queen jumpers that I found in this extended scattered disk. Okay, now I will focus on if we have a kind of memory of the initial shape we can find in the final orbital elements. For this, I have to introduce, well, I will show some typical long-term orbital behavior we found. And to explain them, I first have to introduce what we call the empty ecliptic plane. This plane is, so we have here the red, so this is a celestial sphere. The red, there is nothing red, black. The black line is a galactic plane. The blue line is an ecliptic plane, okay, with a 60 degrees inclination. And the empty ecliptic corresponds to a rotation of the ecliptic of 180 degrees around the galactic axis, okay? Okay, so this, okay. So the first long-term behavior we identify are kind of frozen orbits that are the typical behavior is semi-major axis, which is very small, about 1,000 astronomical units for most of the propagation. And we have, well, the orbit does not change. Only at the very end, while the perihelion is close to the Neptune orbit, and at the end, we have a scattering by Neptune which is stronger than before, which increases the perihelion, the orbital energy, and this allows the comets to be observable. Okay. So what happened here in the celestial sphere? We have here the initial orbits in red. Okay. And we have, we will use for parameter, as a parameter to identify this kind of orbits. So here we have the direction of the perihelion, okay? And we consider the latitude of this perihelion with respect to the ecliptic, which is indicated by a delta, the delta angle. And the delta star angle is the same, but with respect to the empty ecliptic. This is just a way to see how far is the orbit from the ecliptic or the empty ecliptic plane. Okay, we can use also the ecliptical inclination to see how far we are from the ecliptic plane, and we can also use the galactic longitude of the ascending node, because you see here that if the orbital plane of the body is close to the ecliptic, then also its galactic longitude of the ascending node will be close to the ascending node of the ecliptic. Okay, so we have these 4 parameters to understand the geometry of the orbits with respect to the galactic or the ecliptic plane. Okay, for these orbits, the final one is more or less the same. Okay, so we have the same kind of parameters. So at the end, we can identify this kind of behavior with cosine of the ecliptic inclination, which is close to 1, galactic longitude of the ascending node, which is between 0 and 180 degrees. So this the interval is quite large, but okay, the theory is one thing, and then the numerical experiments are different, so we had to use this. And this is characterized by a previous period distance, which is between 7 and 30 astronomical units, just because we need a carbon queen effect, that is scattering by Uranus or by a giant planet, in order to increase the semi-major axis at the end for the comet to be observable. Okay. So this data needs to compute the orbital elements at the previous period distance. Okay. But we can also use the original orbital elements, that is at the period distance where the comet is observed, but going backward into 250 astronomical units in order to retrieve all the planetary effects on their way to the perihelion where they are observable. And in this case, we have the distance with respect to the ecliptic should be small. With respect to the empty ecliptic, it should be about 1.9, okay? And we have original semi-major axis, which should be between 30,000 and 36,000 astronomical units, okay? This is for the first one. For the second long-term behavior, in this case, we have a large oscillation, one single large oscillation of the perihelion distance, okay? But in this case, if you remember the talk by Sławomir before, after one cycle, so the eccentricity is the same. So it means that also the galactic inclination is the same, okay, considering the integrable approximation. But it means also that the galactic argument of the perihelion is the same, okay. But also, for the galactic longitude of the ascending node, its period is only half of the period of the galactic, of the period distance and the inclination. So this means that if you make all this angle, galactic inclination, argument of perihelion are the same, but the longitude of the ascending node is shifted by 180 degrees, you end with an orbit which is close to the to the empty ecliptic plane. But here, no, okay, sorry, I was describing this one. Okay, sorry. We end with an orbit which is close to the empty ecliptic plane. Okay. Okay, so this is what we obtain with this orbit. For this orbit, we have the cosine of the ecliptic inclination, which is close to minus 0.5, argument of the galactic perihelion close to 0, or it's the longitude of the ascending node close to 0. The perihelion is smaller than 7, so because here we don't have the carbon queen effect, okay? So these comets were already inside the Jupiter-Saturn barrier at the previous period distance, and we have original semi-major axis, which is smaller than 23,000 astronomical units. Okay. So if I look okay, to the second long-term behavior. So it's at the end it is very similar to the previous one, except that the variation of the galactic longitude of the ascending node is nearly constant for all the simulation, but we have just a very quick jump at the very end during the last orbital period. Okay, so this is why at the previous orbital period we have this longitude of the galactic ascending node, which is in this range. Okay, and we need in this case a carbon queen effect for the comet to be observable. Okay, just now I have to go faster. We just consider now to see if we have some indication of this long-term behavior in two databases of long period comets. So we have the code catalog by Krolikowska from 2014 on the MPC catalog. So we used these two catalogs and made analysis of the orbital elements. So maybe I will jump the technical details here and just see what we obtain for the distribution. So this is considering here the period distance. We have the distribution of period distance here here it's for the period distance smaller than 7. Okay, so in this case we should have only the anti-ecliptic feature, and here we have for the blue it's for the MPC catalog, red is for the code catalog, the gray line is for the isotopic model, and the black line is for the disk-like model. Okay, and we should have this maxima located in this place. So it is well detected in the MPC catalog in this case. Okay, so we have a rather good detection of this feature for the MPC catalog. For the carbon queen feature that is found in the two other long-term behavior, it is well detected here. So we have to consider period distance between 7 and 31 astronomical units. It is well detected in the two catalog here. And if we consider now the delta measurements, so here, yes, this is delta and delta star. Okay, so here again we have a good detection of the empty ecliptic here with the delta which is close to sinus delta which is close to 1. Okay, for the empty ecliptic here, and again for the two catalog we have a good detection in this case of the empty ecliptic, so the empty ecliptic feature, and also for the here we have kind of detection of the empty ecliptic for this range of semi-major axis. Okay, and we have it also for the carbon queen, the disk model, or the disk. The carbon queen effect here. Okay, we made also this for what we call the unbiased sample. Just we consider comets that are observable after 1998, after the starting of the linear program, and with a period distance smaller than 5 and the total magnitude smaller than 10. And we suppose that all the comets are discovered. So this is what we suppose. We made the hypothesis that it was unbiased. We still have a good detection for the MPC catalog. For the code catalog, the anti-ecliptic feature is not well detected. So, okay, anyway, still to be investigated. So this is okay. This is my conclusion. Just to say that okay, we think that we have a fingerprint of this. Of these two features, this carbon queen process that required initial a disk into the Oort cloud until 10,000 astronomical units. This is for the carbon queen features that we have identified. And also for the anti-ecliptic feature, it means that this disk also was present initially, and we have this dynamics, this long-term dynamics over 5 billion years that should have been preserved in the history of our solar system. So it may put some constraint on the long-term dynamics of our cloud and also on the process that leads to its formation. But okay, still to be investigated, and we will wait maybe for LSST observation, and because there will be a poster about this tomorrow.
Thank you.
Questions from the audience? Yes.
Luke Doan, Southwest Research Institute. Is there a simple explanation why your current flux of comets is 4 times higher in the disk model than in the isotropic model?
Yeah, because in the isotropic model, when we start with the period distance inside the planetary region, after one cycle of caused by the galactic tide, we will come back. We will naturally come back to the planetary region. So this is why it's easier to produce observable comet with this model, whereas for the fully isotropic model, it's much more difficult to have this kind of return to the, well, we don't even return because initially they are not even with the period distance inside the planetary region. But clearly it means that the dynamics caused by the galactic tide, the approximation made by the integral part of the galactic tide should be preserved despite other effects like passing stars, GMC, or this kind of effect.
Thanks. Thank you.
More questions? Yes.
Gustafsson, could you comment on how you would use the Gaia data to improve your model?
For the Gaia data, now we are planning mainly to use them for to improve the galactic time model. Just considering the trajectory of the sun around the galaxy, and to build a T3 model. So that is, we just consider a model of the galaxy coming from the Gaia data, and then once we have this solar trajectory, we can build also the tide that is related to this trajectory and implemented it in our long-term propagation. But it is, well, we have students who is working on this now, so it's under development.
Yeah, Julio?
Yes, Julio Fernandez. The last comment reminds me about the problem that we have with, we tried to model the dynamical evolution along the solar system lifetime, because we don't know very well, and I don't know if sometime will be known, what was the radial excursion of the sun during the lifetime of the solar system. Because we know that the solar system was not all the time at the same distance, at the same galactocentric distance. And this is a parameter that we don't know very well, and we don't know at all.
Yes, no, clearly here the hypothesis for the galactic tides is just a circular rotation of the sun around the galaxy with just a constant parameter of the tide. And we have the main parameter, which is the local density, is 0.1 in our simulation. Well, in the preliminary experiment made by our students, where he has started to model a more realistic evolution of the sun, and the density, so with the radial excursion, but also the oscillation of the sun with respect to the galactic plane. With these two effects, we have the density that range between 0.7 and 0.15 solar mass by parsec cube. But well, after I don't know. We still had to understand how it can affect the long-term process here.
Okay, so let's thank Marc again. We continue with Giovanni Valsecchi, who's speaking, presenting an analytic theory on single-stage capture of comets.
Dai, 5 minuti.
Check. 25 dietro 5.
This is a very old subject, but I hope to say something that you have not heard before today. I don't know. You will see. I'll see. As Alessandro was saying this morning, the typical perturbation when a comet passes within the planetary region is of the order of 10 to minus 3 astronomical units to the minus 1. Now, to produce a comet either belonging to the Halley type, that is with period less than 200 years, or to the Jupiter family, less than 20 years, it takes a long time with this thing. On the other hand, since, as was also mentioned this morning at the beginning, since Lexell had shown already at the end of the 18th century that planets like Jupiter are enormously powerful transformers of cometary orbits, then of course, already in the 19th century, astronomers were studying the single-stage capture. That is the idea that at least the periodic comets that we observed, the few that were known at the time, had been produced by a close encounter with a giant planet. In particular, this applied to Halley-type comets that have very elongated orbits that encounter Jupiter, mostly Jupiter, but also other planets can be encountered, but at very high speed. So in this case, the encounter is relatively inefficient. You need a very close passage to have a transition to a captured orbit, after which, okay, you have an interesting dynamics dominated by resonances and other things. Now, so this is the reason why I thought to apply the analytic theory of close encounters that I've been studying with many colleagues over many years, because this works well if the encounter is really close and if the encounter is fast, in quotation mark. What does it mean, fast? It means that the planetocentric velocity of the comet, when it is close to the planet, is hyperbolic. Okay, so no temporary captures, satellite captures, no things like that. So, so the assumptions, just to fix ideas and to have some numbers in mind, it's a very simple solar system consisting only, this one? Yes. How does it work?
No. That's the point. That's the point.
I have to point it there.
Oh, you want to point? Yeah, you
yes.
point to the screen.
Okay. Okay, fantastic. So assume a simplified solar system consisting only of the Sun and Jupiter Jupiter is on a circular orbit, which makes things easier, and a parabolic flux of comets with flat distributions of perihelion distance and cosine of inclination. That is, all the latitudes of perihelion, if you like, are equidistributed on the celestial sphere. So this distribution reflects in a distribution, in a constant distribution in cosine of inclination. Our guiding parameter, the parameter on which we will keep an eye over all this discussion, will be the Tisserand parameter with respect to Jupiter, of course, of the initial parabolic orbit, and it has this expression. You see, it's a very simple expression containing only the perihelion distance and the inclination. Now, this means that our comets are equidistributed in this plane. The ordinate is the perihelion of the comet divided by the semi-major axis of Jupiter. Of course, we don't consider comets that don't cross the orbit of Jupiter, because otherwise the theory is not applicable. There are close encounters like that, but they are a minority. And, and then in abscissa, we we have the cosine of the inclination, and the black lines that I've drawn are lines of constant Tisserand parameter. This figure tells us that basically if the Tisserand parameter is close either to minus 2 times square root of 2 or to plus 2 square root of 2, there is little room for the perihelion distance because the inclination already does all the job to try to fit the Tisserand parameter. And I have also drawn a couple of lines. This green line here, to the left of it, comets, simply for just kinematic reasons, cannot be captured to Halley-type orbits. And to the left of this blue line here, these lines are easily computed. Comets cannot be captured to Jupiter family. For Jupiter family, I mean a period less than 20 years, not the definition we introduced later of Tisserand parameter less than 2. Sorry, I forgot to say that. So in practice, we have that in this parabolic flux, comets that have inclination of 90 degrees, they basically can have any value of Q, because the third component of the angular momentum is already 0. And there is less and less room as you go far from that condition, so you end up with a triangular shape of the distribution. So this will have to be taken into account if you sum up over the entire population. And I have also drawn the two lines, the green one to the left of which no possibility of transfer to Halley type, and to the left of the blue line, no possibility of transfer, direct transfer in just one shot by Jupiter to Jupiter family. Okay, we will use the theory. Well, basically the extension of Epic's theory that was worked by Andrea Milani, Steve Chesley, Giovanni Gronchi, and myself in 2003, which deals with close encounters in which the small body has a planetocentric velocity hyperbolic. The main tool will be the so-called target plane or B-plane. It's a plane used by astrodynamicists. It's a plane that is centered on the planet and is normal to the incoming asymptote of the planetocentric hyperbola. On this plane, you have already taken into account, in some sense, the gravitational focusing. And on the other hand, if you have equidistributed orbital angular elements, you can think that, like darts in a dartboard, the distribution of the objects colliding with this plane is uniform. So you can average over that. We'll see how we do it. Basically, this theory is not done to save time on computations, because now with the computers you can, but it's just a geometric tool to understand what's going on, basically. So that's the main reason. Of course, it gives you also some quantitative results, which I will explain, but it's mostly to interpret, I would say, large numerical simulations. So, how does this theory work? The part that Epic proposed is just start from the restricted circular three-dimensional three-body problem and make the further assumption that when the small body is far from the planet, simply the planet doesn't exist. So the motion is purely Keplerian, unperturbed. On the other hand, when it comes close to the planet, you don't integrate the entire hyperbola. You just think that there is an instantaneous transition when the object is closest to the planet on the unperturbed orbit to the outgoing asymptote of the planetocentric hyperbola. So it's a geometric construction that allows you to give immediately the outgoing orbit, the post-encounter orbital parameters. Basically, in the B-plane, formalism was introduced by Greenberg, Carusi, and myself in '88, and then there were some later additions to the theory later, because actually we slowly convinced ourselves that the theory was worth pursuing. It was better than it looked at the beginning. So in this theory, okay, we use the B-plane that was introduced by somebody working at JPL in '61, Kisner. And it, as I said, is the plane containing the planet and perpendicular to the planetocentric unperturbed velocity, which is basically the asymptote of the incoming hyperbola. The vector from the planet to the point in which the velocity vector crosses the B-plane is vector B. The coordinates are traditionally called xi and zeta, introduced in this paper. And now what we later understood is that the coordinate xi, actually by chance, was chosen in a way that it is the local moid, that is the local minimum intersection distance, when the two orbits don't necessarily have to cross exactly to have a close encounter. The two orbits may pass very close to one another, and the coordinate xi expresses exactly this fact. And so the other coordinate is simply related to the fact that the comet is either early or late in encountering the planet with respect to the closest possibility that would be the encounter at the moid. Okay? So, okay, this is it. Now, this relationship between the fact that one of the coordinates is the local moid and the other is a timing variable suggests us to look for correspondences between B-plane coordinates of an encounter and the initial condition of that encounter. So suppose we have an orbit, we are given A, E, I, and capital omega, which is an ignorable coordinate because Jupiter is on a circular orbit. In the case of a parabolic orbit, would be Q, E, and omega. Then you are left with only two other variables to characterize your orbit in your numerical integration. One is small omega, and the other is basically the difference in true longitude between the planet and the small body at some time prior to the encounter. Okay, but you can write down expression correct to the first order in these two, in the transformation between these two variables, and you have made a sort of mapping between the B-plane coordinates and the space, basically small omega and timing of the encounter. Okay, you see, it's better to see it than to describe it. So, but before showing it, I would just add something, which is an interesting result of this theory, is that if you ask yourself what is the locus of the B-plane constituted by the B-plane points, such that if the small body encounters the planet and crosses the B-plane in one of those points, then the post-encounter semi-major axis will have a pre-assigned value that you have decided. If you ask you this question, the solution is extremely simple. It's a circle on the B-plane with whose coordinate of the center and radius are functions of the orbital parameters of the small body. So, okay, so there are some properties that follow from this, but now what does this mean in practice for our problem? We want to capture a comet, let's say, to a Halley-type orbit. So we draw, for the initial conditions for that comet, we draw the circle that corresponds to the period post-encounter of 200 years, which is a specific value of the semi-major axis. If the comet passes inside the circle, it will have a period less than that. So it's exactly what we want, okay? If we want to do this game for capturing to less than 20 years, it will be another circle. This one has to be smaller and has not to intersect the previous one. So it's to be completely inside the first one, okay? And third point, if you remember the expression of the Tisserand parameter for a parabolic orbit, the Tisserand parameter, actually, perhaps I could go quickly backwards. It basically tells us that the Tisserand parameter has the same sign, for a parabolic orbit, has the same sign as cosine I. Now, consider parabolic comets with Tisserand parameter between 0 and 2. It can be shown that if you by the mechanism described by the theory, decrease the semi-major axis of this comet below this value written here, A less post-encounter less than semi-major axis of Jupiter divided by T, then the comet must necessarily become retrograde, although it was prograde previously. Okay, it's a very simple condition. It's verified numerically. Okay. So just to show you some figures, I start from the famous paper by Everett in '69. At that time, he had a powerful computer. He computed hundreds of thousands or millions, I don't remember, of comets, all with the perihelion distance equal to 1/10 of the radius of the orbit of Jupiter, all with the same inclination, 27 degrees, all parabolic, and the angular elements chosen at random. So it's an ideal application for what I have described up to now. Jupiter, of course, on a circular orbit. So Jupiter, Everett's comet have T equal to roughly 0.8, which means a velocity of encounter with Jupiter, which is roughly 1.5 times the velocity of Jupiter about the Sun, which implies that traced on the B-plane, the disk representing collision with Jupiter has a radius 3.26 times greater than the physical radius of Jupiter. Okay, so finally, having made all these premises, now this is finally a picture to understand what we are doing. How much time do we have?
Still 15 minutes. 15.
Ooh,
Yeah.
I'm being fast. Okay. Sorry for going so fast. I was afraid of being late. So we have on the abscissa, on the left we have the B plane, and on the right we have a plane that I'll describe in a moment. What there is here, we have the variable xi in radii, in physical radii of Jupiter. Okay, the physical radius of Jupiter is about 10 to minus 4 its distance to the Sun, a bit less than that. Okay, and this is the Moid coordinate, if you like, and this is the timing coordinate. Then in 0, 0, of course, there is a black circle that has a radius of 3.26 orbit. Physical radii of Jupiter, which is the collision cross-section. And then I have drawn 3 circles. The big green circle is the circle that corresponds to a post-encounter orbit with period of 200 years. So if the comet hits the B-plane within this circle, it will be transferred to an orbit with less than 200 years. If it hits the circle inside the blue, if it hits the plane inside the blue circle, it will be transferred to less than 20 years. And if it hits within the red circle, remember that we are in between, T is between 0 and 2, so there is this possibility of orbit flip. The comet will be moved to a retrograde. Now, Everett didn't speak of his post-encounter, but if he had checked the periods of those transferred to orbits with less than 20 years, he would have noticed that the majority, the vast majority, almost all, are retrograde. Now, as I said, one can make a linear transformation from basically xi into small omega, and zeta into, let's say, the mean anomaly of the planet. Let's fix the body before the encounter at a certain longitude, and let's vary the planet. And we are varying in this direction on the B plane, and we are varying in this direction over this plane. And since it's a linear transformation, circles go into ellipses. And so you have the images of the circles on this space. Why bother doing this? Well, because as I said, close to the origin, we can think that the darts on the dartboards are equispaced, are uniformly spaced. But when you go far, how does this thing finish? So all you know is that the ratio of comets transfer to period less than 200 years to, let's say, to comets that collide with Jupiter is, you can compute it from this, but you have no idea of the absolute number. If you transform to angles, then of course the angles vary between 0 and 2 pi, and as I said, the orbital parameters are equidistributed in these angles, so you can have numbers expressing a probability, basically. Okay, I had forgotten to say that the center of this figure is, of course, the ideal collision orbit that collides with 0, 0 in the B-plane. Okay. So, okay, this slide says what I just said. So there is an expression that gives you the probability. It is exactly equivalent to EPIC's probability formula. We have shown that in one of the papers. But the point is that if you, in EPIC's probability formula, you substitute the radius of the planet, because he was only concerned with collision, with the radius of the interesting circle for your transfer, as long as this circle is not too big, so to speak, this works. It's you can verify that it numerically works. Okay, the denominator of this expression becomes 0 either for inclination 0 or for q over aj equal to 1. And in both cases, this is equivalent to a planar problem, and you can substitute with the simpler formula. Now, what's the point? Why am I discussing this? Remember, I am keeping the Tisserand parameter as the guiding parameter. Now, you can get exactly the same Tisserand parameter of the comets that Everard was studying, also with other combinations of small q and inclination. And if you do this, okay, this is the case that Everard ran, okay? But then if instead of perihelion distance equal to 0.1, you say, no, I want 0.5, okay, then you compute that the inclination is much higher, has to be much higher to have the same Tisserand parameter. And what you see is that the picture on the left is exactly the same because it doesn't depend on Q and I, if not through T, okay? But the area of the circle the area of the ellipse in the space of the angles is slightly larger. The proportions are maintained. And if you go, for instance, to Q equal 0.9, it's still larger. This is 3 times larger than that, okay? So you have a way to distinguish between orbits with high perihelion and low perihelion, basically for the same encounter velocity. So now let's try to have a global view. So here I have just drawn the B-planes for T from minus 2.1 to 2.7 in steps of 0.6. And you see that, okay, here is only possible to have a capture into a Halley-type comet. Here also is also possible, because there is a blue circle as well, to capture into Jupiter family. And you go on and on the same. Then you have also the possibility to flip to retrograde orbit. And in this case, you, for instance, for T equals 0.3, you see that the region occupied by comet that would have flipped is much larger than comets that could be captured to Jupiter family, and so on and so forth. Okay. Here I've tried to show as a function of the cosine of the inclination all the cases. For instance, this is for T equal 2.7. The probability has this strange shape because on this axis is the planar problem, I equals 0, cosine equal 1 for the initial orbit. But if you had the other extreme, the perihelion equal to the same major axis of the orbit of the planet, you would be at the other extreme of this curve. What you can do is to integrate at constant steps in Q along this line and get a probability for this type of orbits. And this is, of course, for the green is for capturing to Halley types, blue is for capturing to Jupiter family, red is for flip if it's possible. And you see that there are many orders of magnitude between the extreme, for instance, between this case and this case. On the other hand, in evaluating this, one must remember the triangle-shaped figure that I showed to the end. So you sum up everything together, and you end up with this figure, which is the final one, in which there is, as a function of Tisserand parameter, as promised, the probability of transfer into a Halley-type orbit, okay, is this green line here, probability of transfer into a Jupiter family orbit, and you see there are orders of magnitude of difference, and the probability of flipping, which is, okay, this basically is a consequence of the arrangement of the circles that I showed in this figure with the many compositions, okay? So you have some quantitative results that should be checked numerically, of course, but at least there is a way to horizon yourself in this range of parameters. I'll finish. So this theory, I mean, should be applied when encounters are really close and they are really determinant in affecting the further evolution of the bodies. So the single stage capture of comets, of course, seems to be one of these cases. Another possibility, which I've started to explore, is the capture of interstellar objects through a close encounter, which has a very small cross-section, but still is not impossible. Or it can also, with some caveats, it can also be applied to the ejection of comets that are on more bound orbits in the planetary region towards exterior orbits that may later be affected by galactic tide or other stellar passages. And that's it.
Thank you. Any questions, Pedro?
Pedro, University of Coimbra. Very cool. I have one yes or no question and then two short questions. Did you try this numerically after you've done it analytically? I mean, if you run these darts boards through the circles, do they...
Not yet for the parabolic case, because there are some caveats that I still have to resolve, but I have added it after the references. This is in a published paper, the one on the orbital flips. This is okay. This is the biplane of a hypothetical encounter of Damocles with Uranus. Why this? Because currently Damocles can nearly encounter Uranus. So it's a fictitious, of course, but it's similar to the real Damocles. And you see that I have drawn the collision circle. And in this paper, we were interested in the flip. So I've drawn the flip condition, the semi-major axis. And the black dots are from an actual integration. Now, how do you do that? Well, you simply follow your body and in the numerical integration and try to determine the instant in which it is closest to the planet. So it is at the periastron of the hyperbola you are interested in. And you can compute it from x, y, z, x dot, then you make the rotation back, you make the enlargement due to the gravitational focusing, and you are on the B-plane. Okay? And in fact, the dots you see also in the angular element space coincide. Now, this is a very close encounter. So what I doubt is that going farther from Jupiter when T is close to 2.5, 2.7, I think. Okay, but anyway, it works at least in this regime. This is another object with encountering Saturn. I've forgotten the name. It's 2000 DG something. Again, a flipping object, a possibly flipping object, and you see again that the black dots match the evolution. To show you what happens if you. Okay, this is the last slide. This is another fictitious case. This is Apophis, that you know encounters the Earth in 2029. And if you ask yourself the question, what is this? Now Apophis has a period less than 1 year, but after 2029 will become an Apollo. And of course you can draw the circle corresponding to post-encounter orbit with the same major axis equal to 1 AU, and it's this green circle. The real Apophis passes somewhere here, okay, but it doesn't matter. The point is that the black points done with the numerical integration, as you see, since we are going rather far from the Earth, they start to detach from the circle. Presumably, this is something that will happen inevitably at a certain distance. But anyway, I don't propose this theory to do exact numerical integrations, not at all, just to interpret what you're doing.
So that was the yes or no question. But the second is, so Oort, he got into comets because he had a PhD student in Leiden, Van Voorkom, in the 50s, that was trying to get Oort cloud orbits into short period orbits on a disk, and he couldn't make it work. But now you found a way to actually do this, although the probabilities are very small. But they are not zero. But they are not zero. So what is my question is, could we then calculate a probability, a fraction of the current JFCs? Is there at least one JFC that came from the Oort?
That's not impossible.
Right.
Absolutely not.
Yeah.
But the vast majority will not come from this process.
No.
At least if I had to bet, I would bet on this.
You have a third one? No.
Well, it was the retrograde thing. There's lots of retrograde centaurs.
Yes.
Well, we're finding more and more. And we still don't know very well how they come about. But I was wondering, but the probability.
Of course, there is a process already well described in literature through secular processes, through the eccentric Lido, von Seibel, Lido, papers by the group of Naos and others. But it's not if they can encounter a planet.
This can happen.
This can happen. I'm not saying that it happens all the time. Actually, that research on the flips was motivated by an integration that we did together with Hans, in which we were trying to produce short period comets, but we were a little abundant in T, in particular parameter. We added also objects that had T less than 2. And then we started to find a number, and these were objects encountering the planets all the time, all the 4 planets. And we were finding retrograde cases, and so it came the idea of looking into this to explain. It seems to work.
Ulrich?
Yes, Fernandez. I think there is a valuable exercise to compute the probability of a capture of a parabolic comet in a short period orbit. We know, you mentioned that we know a case that was Comet Lexel, that was about 2.5 centuries ago. But we tend to think that Jupiter family comets are very old comets that have been around for many, many revolutions, perhaps hundreds or even thousands of revolutions. But if there is at any time a certain probability to have a fresh comet in a short period orbit, they would be very interesting for
Yes.
observational
The
purposes.
point is that the probability per revolution, which is what I am showing, may look interesting. But the point is, if the comet is parabolic, each comet is just one shot. If the comet is already on a periodic orbit, let's say of large period, then you increase the number of possibilities of capture. So Lexell was captured, it's true, but it was not on a very far away orbit. Then it was ejected on a very far away orbit. But that's a different story. It was already...
Yeah, Lexell was just a centaur. And that happens all the time, right?
It wasn't
Things
a-
get scattered back and forth.
It wasn't just a centaur. It had a close approach to the Earth.
Before the encounter?
No, after. But
Yeah, well, that's my point. It was just part of the centaur population and had an encounter with Jupiter, and then had another encounter with Jupiter and was ejected. But all JFCs go through the centaur period, centaur phase, and they have an encounter with Jupiter that scatters them in, right? And they go back and forth an average of 7 times, if I remember my paper.
Something like that.
Right, and so that's pretty typical, right?
There was a
Tom?
So there is, a secular way of, right, without a close encounter, of getting parabolic forms into particularly Ollie type comets, but certainly, even shorter periods. So, there's an issue of what fraction,
relative importance.
so given, say, a population of parabolic orbits, what fraction get into Jupiter family via an encounter like this, and what fraction get in via secular effects, and right, Duncan Quinn and Janae, we found that
I'm not
secular
drawing
effects-
any general conclusion from that, just that it is a possible thing. No.
Okay, so let's thanks Giovanni again. And last but not least of the day, so Elke Pilat-Lohinger is talking about the dynamical effects of the passage of Gliese 710 on Oort cloud comets.
Okay, thank you. And Johannes for being invited to this very interesting meeting. And I'm going to talk about...
No, the other way around.
No, the other way. Okay. I'm going to talk about an encounter. Let's go to the future. This is a study of about Gliese 710. It's a K-type star. It has about 60% solar mass, and it is approaching the sun with a velocity of 14.4 kilometers per second. It can be observed with a telescope now in the Serpens constellation, but not by naked eye so far, because it has a magnitude of about 9.7 or something like that. And the first time that it was this encounter has been announced. This was in 1997 by Garcia Sanchez at an IAU meeting in Kyoto, and he showed that in fact here we see a figure from Hipparchus observation, all stars at a distance less than 5 parsec from the sun. And, here, there is this star which enters the Oort cloud, and this is in fact the Gliese 710. Which this will happen in about 1.3 million years. And this observation from Hipparchus has been confirmed by the observation of Gaia. you can see from the different data releases of Gaia that in fact the minimum distance of the star between the star and our sun changes from data release to data release, and the last value it's about 10,500 astronomical unit in about 1.29 million years. So you can get this also if you take the data of Gaia and compute the orbits of the Sun and Gliese 710. This is the blue orbit here. And you will find that, in fact, there is this close encounter, and afterwards the distance of the two stars will increase again. Okay, so a distance of 10,500 astronomical unit means that it goes through the Oort cloud, through the spherical Oort cloud, and it comes, in fact, to the inner border of the spherical Oort cloud. Well, when passing through the Oort cloud, it may perturb lots of comets, because in the Oort cloud there should be 10 to the power 11 or maybe 10 to the power 12 objects. Well, it was this was interesting for us because we decided to apply our n-body code, our GPU n-body code to this event. And of course, we cannot do that. The calculations for that many objects, so we reduced it and calculated the sphere of influence of Gliese 710, in that way you reduce the number of objects, and of course we also considered the comets to be massless compared to because they're much smaller than the masses of the two stars. And in addition, we in fact divided the Oort cloud into different shells. The innermost are the disk and a sort of a flared disk where the star doesn't go through, but through and the spherical Oort cloud has been divided into 4 shells, which is S3 to S6, from 10,000 to 100,000 astronomical unit. If you calculate the sphere of influence, the radius of the sphere of influence for Gliese 710, it's about 8,000 astronomical unit. But of course, in reality, it should look like this because it increases with the distance of the star. But we didn't do that because we are certainly, even if you apply a GPU code, you are restricted to a certain amount of orbits. And so we in fact defined our initial setup for our numerical study by the Sun, the K-type star, where the two stars were propagated with the Gaia data release 3 data. and until a distance of Gliese 710 until 300,000 astronomical units from the Sun. And we've put in the spheres, which are shown here by different colors. In each shell, we've put 42 million objects. All the objects shown here have pericenters larger than 70 astronomical units, because otherwise the influence of the giant planets have to be included. And so, in fact, and this is the direction from where the Gliese 710 comes. And when we calculate, in fact, the flyby until the distance, which is the closest distance to the Sun, so the 10,500 astronomical unit, at this distance, this initial stick, oops, where is it? In fact, looks when at the closest approach like this. So we see, in fact, there is a perturbation in x direction. There's also a perturbation, oops, in y direction. We see the spikes here. Maybe it's better seen here in this plots, in these 2D plots, which show different views of these stellar perturbations, where in fact on the XY axis, in this case the Gliese 710 comes from bottom and goes up, and we see in fact the strong perturbation in X direction, and also the some spikes in Y direction. So the comets following Gliese 710, but we see also from the objects where the star didn't pass, they are attracted by this star, and this is the presentation, the X set direction and the Y set direction. So we see also a slight displacement at the close encounter, at the closest encounter distance of the two stars. So, okay. And here are the results, a summary of the results of the numerical simulations. So, in fact, we had nearly 170 million test comets in our simulations, where about 100 million had eccentricities less than 1, so they were on elliptic orbits. All objects that had initially hyperbolic orbits were scattered out, were escaped. In addition, 22% of the elliptic orbit escaped. From these objects where the star passed, about nearly 66,000 objects had afterwards pericenters less than 70 astronomical units. So for these objects, the influence of the planets will be important, and about half of these objects were perturbed in that way that they are moving towards the sun. So their distance is less than the initial distance. About 24,000 objects remain in the shell, but the perturbation caused larger eccentricity, so the pericenters are closer to the sun, and about nearly 9,000 objects were on orbits moving outwards from the solar system. Then the objects, there were also nearly 5,000 objects with perihelion distances in the observable region. So with pericenters less than 5 astronomical units. And so again, about half of this number moved already inwards towards the sun. About 1,800 remain in the shell as in the initial shell, but with a larger eccentricity, the pericenter distance is closer to the sun, and about nearly 600 orbits are moving outwards. And here we see, in fact, the objects that are moving towards the sun. So we see in purple, these are the objects from S3. So initially they were, the X scale is now logarithmic. So initially they were placed between 10,000 and 25,000. So we see that all these objects are already at distances closer to the sun than they were initially placed. This is the same for objects with pericenter distances in the observable region. But of course, even if they will come in the observable region, it will take a long time after the flyby that they will be really observable from Earth. And they all have inclinations between 10 and 180 degrees. What is also interesting, maybe, that how many of these comets will come close to the Earth or come closer than the Earth orbits, and this can be seen here, and maybe there are about 20 objects which move already towards the sun and have the pericenters close to the Earth's orbits. And as we can see here is that they all have inclinations. So none of these orbits is in the ecliptic. They all have inclinations between 20 and 160 degrees in that case. But there are another 20 objects from that still have semi-major axis in the initial shells. So these are the objects which which have already motions towards the sun. The other which have still semi-major axis, another 20 objects which have still a semi-major axis in their initial shells, but they have higher eccentricities and will also approach this region close to the Earth. This means that it will take still some time until these objects will be, or could cause some problems for planet Earth. But to study this, maybe all these objects have to be computed, including the planets, because if the pericenters are inside 70 astronomical units, as Marc said, we have to include the planets, the influence of the giant planets for these orbits to be sure what's the evolution of the final evolution of these cometary orbits. And so I think.
Thank you. Questions? Yes.
Gustafsson, two short ones.
Yeah.
One, what fraction of comets were captured by these?
By Gliese 700, we didn't look at this. We just looked how many planets, how many comets were scattered inward in this study. But yeah, maybe it would be interesting.
I would think none.
None.
Because once you get encountered, right, they're going to come into the star with a fairly large velocity. And all the star can do is change the angle of the velocity. You can't change the relative because it's on the Kepler orbit, right? So I don't think you would see any capture. I'm guessing.
Well, we didn't study it, but I remember there's a simulation by Susanne Pfalzner et al. About a former, an early flyby. And in this simulation, you see how the small bodies are following the star. So maybe
you have to be in a situation where the orbital velocity around the star, your initial velocity around your star is comparable to the encounter velocity in order to get that to work, because then the velocities can subtract, and then you could have a velocity that's smaller than the escape velocity of the penetrator, or whatever you want to call it. But that's the only way you can get binary transfer like that.
10,000 EU.
Yeah.
Second one, have you estimated how often this has happened during the history of the Sun? A similar event?
Well, as I've shown in the beginning, there was also, I haven't shown the slides of the Hipparcos data. There was also a plot by Garcia Sanchez. This is for the next 2 million years, and when he showed this, there was also a plot for the last 2 million years, and there was, except Gliese 710, no other star coming that close to the solar system. So usually it's a rare event, but maybe.
I don't know if it has been done with Gaia. It could be thousands. Yeah, I don't know if it has been done with Gaia DR2 or 3 again, this same thing, going back.
Right.
Maybe. I don't
Baylor
know.
Jones has done this.
Yeah?
Yes.
Okay.
2018 reference, maybe not the most recent Gaia release, but there's a couple of Baylor Jones works where he's examined
But again, if you look at the statistics that people put into these cloud formation models where you have passing stars, this happens occasionally. Right?
That close?
Statistically.
Yeah?
Yeah, I think so.
So did you scale your results to the normal flux of long period comets to estimate what kind of shower this will be? So it's a 10% shower or 1% shower? Or
no, because in fact,
shower?
if no, not yet, but obviously there are lots of objects the Oort cloud will lose because we found we studied only a narrow region around the
you have to normalize the whole shell.
No, we didn't do that so far.
How?
Yeah, I have a comment. I would encourage you to look at this, what happens outside the sphere of influence.
Yeah.
Because this star is large enough that it will perturb the trajectory of the sun.
Yes.
And as a result, it'll look like a tide to the Oort cloud comets, and even stuff on the opposite side of the star will be perturbed because the sun is being pulled more than they are.
Yeah.
So, sticking yourself to the sphere of influence
we found
not be exactly what you want to do.
We found a slight displacement of the solar orbit. That's right. Yeah. But in this study, we tried to in fact, study as much as objects to be close to a object density, which could be in the Oort cloud, and this was the limit for us.
Bryce Boland from Eureka Scientific. I have a question for one of your plots. You show X, Y, Z, three different plots, the different projections. So the one, yes, this one right here. So why is there kind of a preferred direction for how some of these particles are perturbed? And it's flat on one side, but extended on the other, or the
This
Y
must
versus-
be. This is caused by, well, we started with the computations at the distance of the star at 300,000 astronomical unit. So probably this star already influenced the motion of the comets before, and then there is a slight, as you can see here we have an influence in the other direction of X, and the star is coming from top, because this is the outermost shell, and when it goes through from top to bottom, it's in this area there's more perturbation in this direction, and this is in fact here it passes. Here this is the data when the star is closest to the sun. Here we have a slight change in its orbit, and then it perturbs already these particles in the negative X direction.
So Julio, last.
Yeah, Julio Fernandez. I think just making very quick calculations that the third passage will not change too much the flux of new comets, because you just can make an estimate in this time scale that is about 70,000 years.
Yes, that's right.
In 70,000 years, you will have about 50,000 Earth crossing new comets. And you are saying that this produced injects about 20 comets.
Yeah, but this was only the direct influence of the star when it passes through. So for further, for a longer study, we have to include also the perturbations of the planets to show to show the orbits of the comets on a longer time scale.
Yes. There are no new comets, no?
Okay.
Jan-Erik Wahlund, Institute of Space Physics in Uppsala, nearby. Did you include the possible Oort cloud of the Gliese itself?
No, no. No, we didn't test an exchange of cometary orbits. No.
Okay, so let's change LK and all this.